Hear me okay back there? Morning. Not bad, it's good to see you. Good to see you. Hey, good morning, everyone. My name is Scott Andreas. I'm an engineering manager at Apple in our cloud services group focused on Apache Cassandra. I'm here this morning to offer a retrospective on where Cassandra has been over the past decade or so, and to share some possibilities that recent work like transactional metadata and Accord open up for the database. The features that I'll be sharing today aren't exhaustive, but are some of the ones that I've been a little bit closer to. It's so good to see all of you. I'm glad that we can have an in-person event again, and I hope that we can connect well at the conference. We'll start by framing the context of Cassandra's emergence in the original Dynamo paper, and then I'll take this as a jumping-off point to follow how Dynamo-derived systems like Apache Cassandra evolved. We'll survey what stuck and some concepts that didn't pan out quite as well, at least for us. And then finally, I'll offer some thoughts on what's new and what I see as next in majority quorum databases. This includes an introduction to the new leaderless Paxos protocol developed to implement cross-shard transactions in Dynamo-derived systems that execute in one WAN round trip, which we call Accord. Other features that we'll talk about aren't necessarily committed, accepted, or even discussed roadmap items within the Apache Cassandra project, but maybe they will be. The question this talk poses, though, is whether systems that begin from humble origins, but with a few really uniquely powerful capabilities, can build on that architecture as an asset and slowly close the capability gap with traditional databases through about a decade of hard work. You can bet, because I'm here today, that I think that the answer is yes. So let's dive in. The Dynamo paper and Apache Cassandra, which was modeled after it, were my introduction to distributed systems. I was a liberal arts grad, an early career engineer, just learning how to build services when a colleague shared it with me. Dynamo described a system for storing shopping cart state, functionality that would have typically been served by a relational database at that time, but in a very undatabase-like way. I was fascinated by the path that this paper carved to solve a very specific problem, and the set of scenarios that it seemed to anticipate along the way. I'd love to thank all of the Amazonians that are here and everyone involved in that work for what that paper taught me. So what did the paper claim? The paper didn't call Dynamo a database, and it seemed really careful in not using that word. The system was a highly available key value store, designed with a leaderless architecture, focusing on incremental scalability, properties that were pretty uncommon for contemporary databases at that time. The API was very simple. It stored only opaque bytes and let you retrieve them given the key. Availability was paramount for that system, and it meant meeting an aggressive latency SLA at the 99.9th percentile. But there's a lot that it left out. There wasn't a query language. There was no query planner or optimizer, much of which was delegated to a smart client. Dynamo had no concept of transactions. There weren't indexes, there was no MVCC, no snapshot isolation. There were no rich data types, no aggregations, views, functions, or procedures. The paper didn't even describe a storage engine. It noted that BDB and MySQL were both pluggable options. So if you think about contemporary storage systems that were popular at that time, like Oracle, MySQL, SQL Server, Postgres, these were really glaring omissions for something that acted as a data store. And that paper, about 16 years ago, sparked a lot of discussion and interest in what became the field of non-relational data stores. Dynamo was successful because it took a use case that typically would have been served by an RDBMS. It framed a very specific set of goals, their availability, latency, and scalability. It pivoted its entire universe around those capabilities, and then optimized for them at the expense of features that any RDBMS would have offered at that time. And that raised somewhat of an existential question. What is a database among distributed systems practitioners, along with some really reasonable eye-rolling among people who had worked in the capital D database engineering field for a long time? They were and are quick to remind the world not to confuse a distributed hash table with a database. But some started to wonder if there were more database-adjacent problems that could be solved with an architecture that had unparalleled availability, scalability, and latency characteristics, and also how much people were willing to give up for it. Crucially, a lot of people agreed with that idea, and sometimes a little too readily. If you remember the database landscape around 2010, 2013 or so, and some of the work that followed in Kyle Kingsbury and Jepson's research, that work taught us that many early data stores from that era were dangerously unsafe and failed to provide the set of properties that they advertised, and yet still enjoyed a surprising degree of market success, which surprised a lot of people too. Kyle's still doing this work today, and things haven't gotten a whole lot better. This pattern isn't a new one, though. If you've read it, Clayton Christensen framed it really well in a book called The Innovator's Dilemma, which featured a case study on the disk drive industry at the time of early personal computers. Christensen identified a pattern, and it was that new technology solves a problem in an undeveloped market. It lacks table stakes features that most would regard as critical, but it finds a niche that it can establish itself and succeed in. And then over time, as it gains market share, that technology gains capabilities that are needed to enter minor segments of mature markets, then slowly chips away at that gap while building a moat around what it really excelled at until it can compete with entrenched players. Eventually, those entrenched players retreat upmarket to more sophisticated segments, and the new technology becomes firmly established, gaining most of the missing capabilities while renegotiating with the market what requirements really are table stakes. This process of succession maps really well to some of the transformations that we've seen in the database industry over the last decade. Emerging products missing major features carved out a niche, then buy time to grow what they lack and move into more established markets, building a moat around what made them disruptive in the first place. And this is where Apache Cassandra comes in. Cassandra was co-authored at Facebook by an original author of the Dynamo paper at Amazon. It took many aspects of the Dynamo design, like data placement via consistent hashing, tunable consistency, gossip, hinted handoff, Merkle trees, and timestamp-based conflict resolution. Cassandra added the few features that weren't originally included in the original Dynamo paper, like rich data types and an LSM storage engine. But it sure had a lot of growing up to do. Dynamo's tight framing of its own problem statement was critical to its own success. But what problem space do Dynamo-derived systems like Apache Cassandra try to succeed in today? Most of these are extensions of the design goals of the original paper. For us today, scalability and availability remain paramount, with a pretty incredible range from 3 to 1,500 database instances per cluster. Availability standards are very high. Dynamo's architecture enables Cassandra to deliver 5 nines of availability easily, and especially with multi-region deployments, 6 nines or more. This is only possible because all maintenance operations are designed for zero downtime. And we'll talk a bit more about how the majority quorum architecture contributes to that in a bit and why it's so critical that we preserve it. Cassandra also targets wide distribution, with databases deployed active-active across 5 regions. It can store many petabytes of data in a single database and serve millions of queries per second. It offers strong consistency and linearizable transactions. There aren't many databases that can do these things in our industry, especially few that are open source. So within our innovator's dilemma frame, we've moved up market a lot from Dynamo's origin, which had very loose guarantees and a very slim API. A question that we can ask ourselves is, how far can we push this while building on the strength of Dynamo's scale, availability, and distribution characteristics? It's useful to distill some of the most important Dynamo properties that help Cassandra get to this point, because we probably want to double down on those. They're what have really made us successful. For Cassandra, these are Dynamo's leaderless architecture and majority quorum design. The simplicity of the leaderless architecture was brilliant. It avoids bottlenecking on a distinguished transactor. It eliminates the impact of gray mode failures in the case of a leader on failing hardware. Think like a bad disk that's slow to respond or a dead fan that results in thermal throttling that might not otherwise be detected. It eliminates the risk of blips during leader elections or the impact of a failed election or loss of a leader. Queries and transactions can be initiated and led from any region, active-active. With 3 or even 5 regions, this enables Dynamo-derived systems to remain available and consistent during even major disruptions to internet infrastructure. Transactions can be initiated from any region with equal latency. And crucially, failure domains in Cassandra aren't global, but they're scoped to a small set of, say, 3 replicas for a given key. And in a cluster of, say, 1,500 instances, this confines the blast radius of concurrent hardware failure to just 0.2% of the cluster. But individual hardware failures have almost no impact at all, thanks to the next attribute that I mentioned a moment ago, which is Cassandra's majority quorum design. This approach was a great design to build a database around. In majority quorum systems, the probability of failure is a function of the likelihood of concurrent failures of replicas across multiple failure domains. That's a powerful concept. Cassandra's data placement strategies can be made aware of the failure domains of the data center and the cloud that they're deployed on to achieve even greater availability. For physical DCs, this means replicating data across rack, power, and networking failure domains. The database's awareness of the physical topology of the data center makes concurrent replica failures incredibly rare. Similarly, control planes that are aware of data center maintenance activities can greenlight or deny non-essential maintenance, like upgrading software on a switch that would take down a rack or deploying a new software release, which can even further mitigate the risk of concurrent failure. This approach maps really well to cloud concepts too, with availability zones and regions mapping similarly. Apache Cassandra achieves strong consistency by ensuring that all reads and writes are served by overlapping quorums, and in cases where replicas disagree, blocking read repair of the most recent value before returning to the client and publishing that value outside the system. This produces a consistency contract that matches what a user would experience when querying a single machine database like Postgres at a non-transactional isolation level. Together, Dynamo's leaderless architecture and majority quorum design are at the heart of Apache Cassandra's scalability and availability, and contributors to the project have designed approaches that enable us to achieve the consistency and even linearizability characteristics of traditional databases. This took a long time. So thinking back to the innovator's dilemma example of moving up market by gaining features, let's take a look at Cassandra's evolution of these database-like features that were built on a Dynamo origin. In 2011, Cassandra gained an SQL-like query language called CQL with rich data types as well as secondary indexes. CQL was unique among query languages in that it was designed to allow users to declare a data layout on disk that was optimized for efficient storage and retrieval of what the user had wanted to store, rather than something that's meant to be passed to an optimizer for planning and execution. And this is, I think, one of the genius elements of CQL. Like, if you think about SQL, the goal was to refactor queries in terms of a relational algebra that let the database construct a plan and execute it. In this case, CQL's design, which focused on declaring the data layout and retrieval strategy, mapped very directly the mechanical sympathy of how data was stored on the disk to what the user was trying to access. In 2012, the database properly supported strong consistency, and in 2013, added linearizable transactions for a single key in the database built on Paxos, which we'll talk more about later. In 2015, Cassandra grew a new storage engine, and now Cassandra is gaining strong HTAP capabilities, such as deep integration with Apache Spark, making it possible to query the database at over 600 gigabits a second, which Dinesh presented on yesterday, as well as distributed transactions with strict serializable isolation across multiple tables. That's all pretty exciting, but what's with this little gap here in the resume? During this gap, the Apache Cassandra project confronted the quality debt that plagued many non-relational databases at the time. And this took several years, which you might have noticed during Josh's presentation yesterday on the health of the community, which touched on some of the time that it took to ship Cassandra 4.0. Becoming a database that competed at the upper tiers of the market really required foundational work to make the system safe and correct. One downside of Dynamo's resilience was that its design can be devilishly good at hiding inconsistency and fiendishly hard to investigate what happened after the fact. Property-based testing was among the most effective strategies that the community adopted to address these issues. These tool chains work by fuzzing a Cassandra cluster with randomized queries and schemas while keeping track of the responses that the client has observed from the server. These responses provide a signal to the model that enable it to differentiate between what should have been allowed to happen versus what could not have happened inside the database. Some examples would be that acknowledged writes can't be dropped and must be observed by later reads, or that timed out writes may or may not be visible to a later read because they're indeterminate. Maintaining this model provided the basis for asserting correctness, a test that's great when paired with fault injections like cluster restarts, range movements, and instance replacements. These tests can be executed both on a developer's workstation or at scale in the cloud, which really helped the project improve reproducibility given deterministic seeds. Simulation was another technique that project contributors adopted, and this one was invaluable for validating the evolution of our Paxos implementations. By simulation, I mean generating randomized input, then taking full control over the execution of Cassandra and modeling it as a single-threaded program, taking control of all aspects that could introduce non-determinism, like time, like disk I/O, like thread scheduling activity, and lock acquisition, to give you what effectively behaves as a single-threaded database. This means that from a given seed, regardless of the hardware or operating system platform, execution of the suite is guaranteed to be completely deterministic. This is a really powerful primitive. In the context of Cassandra's transaction subsystem, we simulate thousands of hypothetical clusters and topologies and millions of Paxos transactions paired with a verifier that asserts the linearizability of the result. Simulation enables at-scale fuzzing of consensus algorithms with near-instant local reproducibility. This has dramatically improved our ability and confidence in evolving Cassandra's Paxos implementations. These techniques have also helped us identify and resolve over 30 critical bugs that resulted in data loss or incorrect query responses, and today provide us tools to think with while we develop new features in Cassandra. In the early days, the project also used to deprecate features in a manner that required action for many users and resulted in users often running database versions that were somewhat far behind the most current release. But we learned that heavy deprecation of features forces work onto those users, work that they often won't do or can't do in the event of a vendor-deployed product that uses Cassandra, which means that the project risks losing those users. That meant finding strategies to carry forward some previously deprecated features to enable drop-in upgrades across versions, something that we value pretty highly today. And finally, we had some reflecting to do. We've come this far, but what features are we missing? There's a lot of good stuff ahead, some of which you probably heard about so far this week. You might have heard from Piotr's presentation that storage-attached indexes are coming to Apache Cassandra 5.0. SAI is a scalable partition local index. These indexes achieve feature parity with existing secondary indexes, but with much better performance, storage, and operational characteristics. Because they're implemented as SS-table components, they get zero-copy streaming for free, meaning they get shipped straight over the wire at link rate, rather than triggering expensive index rebuilds as they're streamed in. The initial release adds support for AND queries, numeric ranges, fixed-length numeric types, text indexing, and inequality queries, as well as optional case sensitivity and Unicode normalization. Soon, we expect to incorporate prefix like and or queries that you might be used to in other databases, as well as case sensitivity and Unicode normalization. In the same way that Cassandra moved upmarket from a Spartan feature set 10 years ago, SAI will enable indexes to rapidly gain new capabilities through incorporation of other functionalities in Lucine's search and indexing libraries, another Apache project that the Cassandra community can greatly benefit from. Transactional cluster metadata is a down-to-the-studs remodel of cluster membership in Cassandra that's designed to resolve some of the database's oldest and most persistent problems. As Alex presented yesterday, gossip and epidemic broadcast were en vogue around 2007 distributed systems research. And they're fun techniques and solutions for systems that might have 100,000 or more nodes, but that typically doesn't describe most Cassandra deployments. It was impossible to build correct and reliable state machines on gossip because that model relied on one node deciding to do something, like claim ownership of a token and stomping on it, and then telling everybody else, who then have to take compensating action as they learn. You can't build a great state machine on that. TCM enables safe and rapid modifications to cluster state, which improves Cassandra's elasticity. It eliminates schema divergence. So if you've ever found that schemas diverged after making rapid DDL changes, or maybe you used a library like Liquibase and then had a mess to clean up after, this is a problem that just simply won't happen anymore with transactional metadata. And if you've got a lot of scaffolding that orchestrates operations in Cassandra, like instance replacements, repair, upgrades, and so on, this work may enable the database to take responsibility of some of those features, in future releases. But this last one here is likely to be pivotal to the future of Cassandra. Today, Cassandra distributes data based on tokens, usually via random partitioning. Ordered partitioning is necessary for cross-partition ordered scans and joins, but to do it as a database, you have to be able to split hot or dense ranges. TCM provides the machinery that might allow for efficient range splitting in a future release, as well as a transition from token ownership to range-based ownership, where those ranges could be redefined and moved. This is going to be a super heavy lift, but if we complete it, it would enable Cassandra to become a completely new kind of database, pivoting from being a multidimensional unordered map to an ordered map, much like Spanner and DynamoDB. Next is witness replicas. This is a feature that was controversial a few years ago, but I'd love to share more about why I find it extremely important to the future of Cassandra. If you've ever had an exec or finance partner come to you and say, we need to get our cloud costs down, you'll probably care a lot about this. This feature could save you about 30% on your storage costs. Today, Cassandra couples quorum size and replication factor. They're the same to the database. That means that if you have 3 replicas and 3 data centers, you're paying to store 9 copies of the source data. And if you deploy on top of a replicated block device like EBS that replicates data a further 2x under the hood, those 9 copies of data are actually 18 copies of the original data. This is incredibly inefficient. Witness replicas build on a fundamental invariant of incremental repair. IR guarantees that the repaired set in Cassandra is immutable and consistent across replicas. Because the repaired set is guaranteed to be identical across replicas, there's no point in querying more than 1 copy of it. This means that we can drop the durable RF from 3 to 2 without impact. And then we only have to read 1 of those copies as well. Quorum reads are guaranteed to be consistent if they include 1 consistent copy and a quorum of the unrepaired sets. So this feature shift is experimental in Cassandra 4.0, but contributors are working this year to bring it up to scratch and to remove that experimental tag in a future release. So please do not go turn it on now, but think ahead. Saving 30% on storage is a pretty big deal, and we hope to have more to share in a year or so. Distributed ACID transactions are our next focus. Some of the design goals that we've established are as follows. We think users should be able to transact over any subset of keys in the database, including across tables. We think that Cassandra should support strict serializability, the strongest level of isolation possible. We want to achieve optimal latency, one WAN round trip for all transactions under normal operation. We also want optimal fault tolerance. The latency and performance must be resilient to a minority of replica failures. In terms of scalability, we don't want a single point of coordination or a bottleneck introduced. We also value portability as an open source project. No specialized hardware should be required by the feature. All of these sound like some of the capabilities that Dynamo was built around, and a lot of that are what you see echoed today in our design for the feature of distributed transactions. To achieve this, project contributors have designed a new Paxos protocol that's harmonious with Cassandra's architecture called Accord. The name Accord is a nod to Leslie Lamport's part-time Parliament paper that introduced the original Paxos algorithm, here adapted to broker consensus between parliaments, or sets of replicas that form a consensus group. Think of the name like a grand bargain between parliaments. Enabling transactions over the whole of the database without a leader means that members participating in the Paxos round may vary from transaction to transaction. So when I say leadership here, leadership is scoped to the coordinator of a single transaction, just a single query. Accord achieves this via hybrid logical time and without specialized hardware or time distribution infrastructure. Transactions execute in one round trip if a sufficient number of replicas are available, falling back to 2 round trips in rare cases. We validated the protocol by specifying a formal proof of the design and asserting linearizability by a simulation of millions of transactions and thousands of logical clusters in the software as implemented. But that still doesn't mean that everything's perfect. So we've continued to collaborate with academic researchers who have identified a couple additional problems with the protocol, then suggested solutions to those. I've never received a bug report in my career in the form of a 3-page LaTeX typeset document, and it was stunning to get that from a group and then say, also, we can fix it. So we value that research collaboration very much as well. There's a link to the paper on this slide. You can also find it on the Apache Cassandra Confluence wiki. So a lot of distributed databases use leader-oriented protocols like a distinguished transaction manager, multi-Paxos, or Raft. Why is Cassandra thinking leaderless? Well, that comes back to the Dynamo architecture again, which presumes no distinguished nodes. This means that every instance operates as a peer. This eliminates bottlenecks on a leader, it avoids gray mode failures, and it leaves a path for scalability if you bound the size of the consensus set that you're transacting over. It also preserves the design simplicity of the database that's at the heart of about everything that Apache Cassandra has achieved. For multi-region applications, it also enables initiating transactions from any region with predictable latency. Active-active apps can issue transactional rights from any region without having first to route them to a primary region, unlike multi-Paxos. Finally, Accord achieves single round-trip latency, meaning the same network latency that you would incur from a read or write at quorum. This speed improvement, down from 4 round trips for writes just a year ago, will make a new class of applications possible. And when you think about distributed transactions or even just a linearizable write becoming as cheap as a quorum read or quorum write, that opens a lot of new possibilities. So I shared this slide yesterday during a keynote with Patrick and Ekaterina, but I'd like to zoom out a bit from the protocol to think about what impact this work can have on Apache Cassandra as a petabyte scale database in relation to the wider field. With this work, Cassandra will become the only distributed database that can scale to petabytes of data, offer strict serializable isolation, can be deployed in any data center or public cloud, offers the availability and performance advantages of a leaderless database, and single round-trip latency for transactions, whether single key or multiple, local or remote. This slide doesn't mean that Cassandra is the very best database for all applications. There are tons of other characteristics that one could optimize for that aren't captured here. But the set of capabilities is incredibly compelling and something that we wouldn't have expected to be possible at the outset, and something that I certainly don't think was anticipated by the Dynamo paper about 15 or 16 years ago. But there's a lot ahead. There are a lot of new possibilities that distributed transactions open for us. Strong transaction primitives open new possibilities for Dynamo-derived systems, like rethinking indexes. An index could be modeled as a transactional mutation to a base table and a derived table. The transaction subsystem composes well with SAI today and might allow us to build even more on top of SAI in the future. They let us rethink materialized views, a feature that the project needed to retroactively classify as experimental. You could think of modeling a materialized view as a transactional mutation to a base table and a derived table with a predicate. They provide a basis for enforcing foreign key relationships within the database, something Cassandra has never been able to do. They could be a primitive to enable Cassandra to support multi-version concurrency control or even snapshot isolation via something like an epoch visibility protocol. Auto-balancing data placement solves the biggest problem with Cassandra's byte-ordered partitioner. This lets us reimagine Cassandra as a multidimensional ordered map with keys sorted within the cluster according to their lexical sorting. Snapshot isolation and ordered partitioning are building blocks that could enable the database to support features like cross-table joins. This may enable Dynamo-derived systems like Cassandra to support a large number of even relational use cases. All of these things can be possible by reimagining a Dynamo-derived system as a transactional database. So we've come back to our frame, a cycle in which disruptive innovation slowly moves upmarket after carving out a niche and gaining new capabilities while building an impenetrable moat around a core competency like scalability and availability. But the news isn't all good, because when you get to the end of the book, you see that once you reach the top, there's usually another technology that's maturing right behind you. Some example moats for future databases might include things like hard multi-tenant isolation, making exceptional use of tiered or disaggregated storage, or full SQL support. I think that all of these could be built in Apache Cassandra, but they're things to think about because you've always got to watch your back. Until then, though, we should be really proud of what the Dynamo architecture has enabled us to build. A database that can serve petabytes of data and millions of queries per second with up to 6 nines of availability, one that can replicate active-active across 5 regions, one that can be deployed in any data center or public cloud without specialized hardware, one that can execute leaderless transactions across the entirety of the database from any region, and one that can be downloaded, learned from, or modified by anyone. That's a great foundation to build on. Thanks all of you for your time today. It's great to see you here in person. We've got about 3.5 minutes for questions, if there's anything that folks would like to ask. Thank you.
I'm really excited about all the changes to Apache Cassandra, but I wonder, do you ever get to the point where you stray so far from the original ideas about Cassandra that it's not Cassandra? I'm curious what you think about that.
That's a great question. The question was, do you ever, as you evolve the database and gain new features, do you ever risk forsaking the foundations or straying from what you were? I think that in any software system, there's always kind of a constant renegotiation of identity that's usually based on where you've come from and what you need to become. And now and then, some of the things that you valued in the past might matter a little less in the future and need to be rethought. And there are some examples of that in Cassandra's history, like replacing some foundations like gossip with things that are fundamentally transactional. There's been a shift from a focus on eventual consistency to strong consistency and linearizability. I don't think of those things as necessarily forsaking the history of the project so much as becoming what we need to be in light of where we've been. Yeah.
Let me get
Can
I have you use something?
Oh, I'm sorry. Yeah. You mentioned relational, Scott. Can you talk a little bit more about that? What sort of use cases Cassandra might be able to address and which ones it may not?
That's a great question. So I think that if we were to try to bite off, becoming a fully relational database, at least right from the beginning, that probably wouldn't be a good lift. But if you think kind of about that frame of negotiation with the market of what features are required, I think that there are a lot of semi-relational capabilities that are really easy for Cassandra to gain. So if you look at APIs like DynamoDB, which aren't fully relational, but which do allow for some cross-table activity or cross-partition activity, people have been very successful in building on top of that API. So if you look at distributed transactions as features that allow you to enforce things like referential integrity constraints across tables, or the possibility of a cross-table join, if we were to move to ordered partitioning in the future, I think that people can express a very high degree of traditional relational applications in the database. That's a bit different from having a full ANSI SQL grammar that's capable of common table expressions and 14-way joins and aggregation that you might have in a more traditional Oracle-style database. That's probably not a good goal for Cassandra, but I think it gives us at least a path to move a little further up and to the right. 50% of the relational market? Maybe by volume. We've got about 30 seconds for one more question.
Actually, more a comment. One other feature that's new to Apache Cassandra that people may not know, and it's pertinent to this, is vector search.
Absolutely. Thank you for mentioning that. There's so much that's in 5.0 and coming after in 5.1 that it was difficult to get all in one presentation. Vector search, I think, is a really great example of Cassandra building upon capabilities like SAI to evolve features that are coming and needed by new markets like artificial intelligence. Thank you all so much. We've just hit our time, but I would be happy to connect with any of you in the hall and would love to chat with you at this conference. Thanks again.
This can just go in your pocket or on your belt. Cool.
Hey? Yep. Yeah, is that working? Cool. Thank you. You should come sit at the front, so if you walk out, you can do it really slowly and walk past everyone.
What's center? Here? Oh,
Yeah.
I got a t-shirt if somebody has a good question.
All right. Is it the T-shirt you're wearing?
No, wait.
Well, if it's a really good question, it's the T-shirt you're wearing.
I'll take the shirt back. No, it's a vector shirt. It's a vector search shirt. If you get a couple of good questions, I'll give them.
Cool, cool. I just had Scott Andreas say SAI and transactions are the future of Cassandra, which was kind of useful. I was like, if everyone stays in this room.
Yeah, just step. I'll tell you about it. Yeah, I got a bunch of these vector shirts.
All right, let's have a look.
These are XLs, but I got some larges in here too.
All right, getting rid of the gear. There we go.
There you go. It's the future. You might have to iron it. Yeah. Real stubborn. What size are you? I'll be ready for you. I'll take it. I don't have any. The all size, like the spandex. Chad looks good in spandex. I follow his Instagram. Yeah, so how good is the question? The pants? The spandex pants? Well, yeah, we're just gonna have to judge that on a case-by-case basis. Yeah. I don't know if I want to go to space anymore. You know, you got the code of conduct? Yeah, I was gonna say, I'm gonna follow code of conduct violation.
Okay, we'll get started in a few seconds. You're right there.
Yeah, I am just like your worst nightmare. I'm just gonna take notes too.
You weirdly like my worst nightmare. Okay, let's get started. My name's Aaron Morton. I've been involved in the Cassandra project since the middle of 2010, and I've spent my professional career since the beginning of 2011 just focusing on Cassandra. Work at DataStax now. And what I want to talk today is about how we made a JSON retrieval API. So there are other, let's get this clear. There are other document-based databases out there that have set some standards, and some of that is around usability. And we would like to see how we can be a bit more usable for people in the Node.js community. So today we're going to talk about the requirement of what we were trying to do and try to understand how the JSON data model works, so we can map that over to these two features that are the future of Cassandra, secondary indexes and transactions, which sounds pretty weird. I've been doing this since 2010. Cassandra isn't big on secondary indexes and transactions, but if you're just in this room listening to Scott from Apple talk about the future of transactions and secondary indexes. Then we'll go and look at how we can do this now with our data model of storing it and how we have to deal with the updates. So our goal here was to make something that a Node.js developer would expect when they're storing data. Back in 2005, when I lived in London, Honda had this advertising campaign for launching their diesel cars called Hate Something, Change Something. So in the spirit of hate something, change something, we're going to go learn about the JSON data model and how we can make Cassandra deal with it. And on that pathway, here's what's important. Functionality is more important than performance. We will get to performance. Performance will be good enough and we will make it better. If there's something hard to do and it makes Cassandra and SQL better, then we should really put in the effort if it's hard. And we had to work out what that Node.js developer was looking for. We don't have a clue. We don't have any Node.js developers in using Cassandra. So we partnered with this project called mongoose.js. It's an object document mapper on NPM. And to say it's popular is an understatement. It gets about 1.8 to 2 million downloads a week. GitHub claims there's 3.8 million dependent repos out there using it. And Valery Karpov, the author and maintainer, is a great guy. And we worked with him to understand what is the back end someone writing Node.js is looking for. All right, into the data model, learning about JSON data model. Well, it looks pretty simple. I've got a map, I've got names, I've got values, they have a type, number and strings, but there's only one type of number, so 1 and 48.8 are the same data type. That's kind of weird. There's a null, but the null is not typed. It's an untyped null, kind of like a Python null. So maybe I could just put this into a table, because we're coming from Cassandra, there's tables and things. This looks all easy. Now I'm going to add on an array. So I've got an array of things that look like numbers. Maybe they could be anything, not just numbers in there. So if I talk about this in a table perspective, I could have a CQL list or something like that to hold an array, but I don't know what's in the array. My example here are just numbers. Okay. To add a bit more complexity, we could put a sub-object into our JSON document here. So address points to an object, and that object has other things in it. Okay, bit harder. If I was doing this in a table mapping, maybe I could have another table for the sub-object, or I could use a CQL map to store the sub-object. It's getting harder. And then when we try to go across documents, it just gets crazy. So in the document on the left, the age is a number, 48.8, and in the document on the right, the age is a string. So which is it? Is age a number or a string? Well, there's no rules. You've got the situation of some things, but what did we learn? So a document or a JSON object has a number of fields in it. Those fields are identified by a name. That name has one or more parts to it, address, dot, suburb. Those fields have data types. They could either be a scalar type with some basic types, and null is a type, or they could be compound data types, and you've got objects and arrays, and you've got an unnamed implicit object at the root, like the document. And across documents, this is kind of polymorphic-ish. I know across two documents, they've both got a field called address. One of them is a string and one of them is an object. All I know is that they're of type value. Right. Next up, how do people think about being able to pull this data out? And again, there are other examples in the industry of how people think about this. One of it is JSON path. I don't think JSON path is very easy to understand. This is a typical sort of query. It looks pretty easy. Go and find one document where the filter where the name equals, I guess, Aaron. Easy. I could add to this. So now my filter clause is two operations. I'm going to guess they're joined with an and. And for age, I've got not just equals, I've got some type of operation I've defined. To add a little bit more complexity, now I've got 4 operations running against in this filter. They each have a path that they're talking about, that field name. And there's a couple of comparison operations. One looks like an existence operation, so does the isHuman field exist in the document? And another is an array operation. Find me the documents where fav numbers is an array of size 3. So the complexity there is growing. And now I get to the next annoying part. All right, so on the left, go and find documents where age is equal to the number 48. And on the right, go and find documents where age is equal to the string 48. Which one do you want? Do you want me to treat it as a number or a string? Well, do some learning again. Our filtering has a number of expressions. Those expressions can either be logical or comparison expressions. They are basic logical expressions such as and or. Our comparison expressions, we point to a path and we say, what's the operation? It could be a comparison, equal to, greater than. Be a logical operation. You can do element operations such as does the element exist? Find me all the documents that have the isHuman field. I don't care what value it is. And there can be operations on arrays, which are matching the contents of the array, finding arrays that have array, finding documents where the array contains one thing. or finding things where the arrays of a specific size, operations like that. And then this polymorphism-ish type thing that JSON does, we're going to use the expression to tell us what type we should be locking in on. So if you say equals 48 the number, I'm going to go find documents where it equals 48. If you say the string, I'm going to look for the string 4 and 8. We're going to just kind of trust that the clients sending us requests are adults and they know what they're looking for, and if they're getting confused between numbers and strings, there's nothing we can do about that. Another part of this is that most of the time, right, there is a strong thing like Mongoose that's making the schema. So people are defining classes, they're just using something like ODM, and we're going to get normally we're going to get all the data will be the same. All right, last part of this learning step. What do we have to write? Well, here's an operation. There are basic inserts that do overwrites, and everybody in Cassandra land knows how inserts work. That's easy. But things get a little more complex. This is where functionality trumps performance. So what this says is, go and find me the document where ID equals 1, and that update clause says, add the field is old and remove the field is human from the document. So I've got a couple of operations happening there in that update. This is getting a little bit harder because we don't do this. This says find the document where ID equals 1, add the field is old, go to the field age, treat it if it's a number. I want you to set it to be the maximum of its current value or 50. That's a read, modify, write operation. You can't even do that in a CQL update. You can't do CQL field equals field plus 2 unless it's a counter. All right, now we're getting a bit more complex. This says find the document, go to fav numbers, it's an array, add 22 and 33 to it if they don't exist. So that's what $add set, add to set says. So again, we've got a level of complexity in the update operations, and we've got a bunch of read, modify, write things that are going on. And these are things we don't like to do in Cassandra. This is all of the things that I could possibly want to do in this find one and update. So find the document, update the is lock field to be the max of its current value or 1. Give me a projection, so return back to me the resource and is locked fields from that document, and return it back the state it was before you did the update. These are all the capabilities you can do in find one and update. So this is how you could implement a distributed lock. It's basically doing that. And again, that's like the level of complexity there. From CQL, we're used to the idea of just being able to do a no-look write and just override everything. All right, so what did we learn? We've got documents that have updates. Those updates can be on fields and arrays. Our updates require the document in memory because we have to be able to make read, modify, write, and decisions about what the document state should be based on its current state. Inserts, by definition, we already have the document in memory, so from a Cassandra point of view, we can just keep rewriting and things again and again, because we always have it. And we'll see that in a minute. Okay, the C* features that are actually useful for this. The talk before here, Scott was saying SAI is great, and it is, and it's the future, and it is, because all the vector stuff runs on SAI. And it's good after all these years to have good secondary indexes. And lightweight transactions, Paxos and Accord are the future as well, which is really weird. Briefly touching on SAI, third time trying for secondary indexes in Cassandra, available in OSS 5. Very efficient at being able to deal with multiple indexes on the same table. We'll see a chart about that in a minute. And very high performance. They've got and or support. So whether that or support is in the version that's in Cassandra 5, I've not kept up with everything, but it's coming. Oh, JD's shaking his head. It's coming, and we're going to see the list of things that make SAI better that we've uncovered in this. So yeah, in the real world, this is maturing and technology. This is from CEP7. SAI was one of the first things to go in that process. You can see the blue line at the bottom. As you add more SAI indexes, you are not using a linear amount of additional disk space. It is very efficient at being able to index multiple columns on a table. And that's really important when we go and see the monstrosity I'm going to show you shortly. Also on that CEP7, there's some of the performance numbers here. This is reading 4 billion rows. I don't know all the details of what it was. It's on CEP7. It's fast, and other people are making it faster. That's always a good situation. Quickly, if you haven't seen them, make a table, create a custom index. You can put it on a text, a number, a date. I've included some of the options there for text indexes. Coming soon as well will be leucine tokenizing of your text fields as well. Now the really exciting part, I can use those like a regular database. So I can say where name equals Aaron, and that's powered by the SAI index. But in those last two examples, I can put two terms into my where clause, and SAI will go and read both of those and do the join for me, and do it smartly. So it's not a sequential get one and get the other, it's parallel work. And it can do the same with OR. So when we found all this, and this was great stuff, we also looked at collections. So I can put them on maps and sets and lists. I just haven't included lists here because we don't use them. You can have 3 different types of indexes on the map. You can index the key, or the keys, or the values, or the entries, which is the really useful one. So you can see if I've got a map here of metadata, I can index and say, get me all the rows where metadata topic equals monkeys. I can put that together in multiple clauses. It's starting to look pretty cool. And I can do a set test as well to see if the set contains a value. Okay, and now on to lightweight transactions. So being around since Cassandra 2, they are used in a lot of places and relied on at scale that probably you'd be surprised about given their reputation. In Cassandra 2, they came in Cassandra 4.1, there's a new version which is supposedly 50% faster, and in Accord, it's going to be more better performance, so it's basically the same performance as a normal insert, in most cases. So we now get to have better consistency, which is handy because some of those use cases for Node.js, users expect to have primary key constraints, and we just went through all the need for read, modify, write, in order to have all the functionality. So quick example here, I can do an insert and if not exists if there are no users with the username, the beard of Zeus. And I can also do an update and only change the value if the value is the same as what it was previously. All right, we've got the building blocks now. We've got a pretty good understanding about the JSON data model, how we need to store it, how we need to read it back. And we know that there are these features that are in Cassandra now and are getting better. SAI is getting better. Our transaction support is getting better. So we can put these two things together and have something that will get better in the future. So we came up with this idea called super shredding, which goes through 3 steps. We're going to walk through the JSON document, take note of the nodes in it, work out that path name, so it's user.name or something like that, understand the data type that it is. Then we're going to look at all the types of operations you could want to do against that and try to work out what data structure we need to store for that, and do we need any extra metadata. So we're going to say for the exist clause, put that in a set because we want to go and look at all the fields we can test. We'll look at that in an example. We want to put it into one row of CQL so that SAI query planner can go and do its business. It's actually pretty good at working out how to run those queries. So we always want it to be in one row. So if we have this document here and we have the isHuman tag, the isHuman field, we see for $exists, we just need to store a set that has isHuman in it, and then we can go and query to find that back. All right, so the next slide has this data model. We've improved it. This is the easiest way to explain it. And I do have people send me emails and things at work about some of these things. All right. Yeah. So let's break this down. There's really 2 things we need to do. Store the blob and maintain some way to be able to pull the data back. The primary key is a tuple here because the ID of your document could be any JSON scalar value. So we have to encode that. String 48 is different than number 48. The TX ID we use in the transactions we'll see shortly. doc.json is where your blob goes. All the others are data structures, maps and sets that together allow us to implement all of the functionality of the API by being able to go and pull those up. We'll go through some examples in a minute. This is even the worst part. So then I go and put all these SAI indexes on there. SAI is going to be slower, is going to take more effort on the writes. That's how databases work. And we will work to improve this. But we now have a good understanding of what it's like when someone puts too many SAI indexes on the table. All right, bit of a worked example. We've got a document, and we want to be able to serve the exists filter, which basically says, find me all the documents where isHuman is defined. I don't care on the value. It could be null, it could be a boolean, it could be a string. So given the document at the top there, we do an insert, and I've just pulled out the exist keys. It's a set. We're walking the document. We've got all the paths, and we go and insert those into the supershredding table. And then when you come back to do a read, where isHuman exists as true, we go to that set and say where set exist keys contains isHuman. Now, SAI in the current installation cannot do not contain, so that's coming as well as one of the things we've added. So we'll see that at the end. But that allows me to do a really simple one. So what about a more complex query? I've got isHuman, I've got the age, so we have a map of all of the numeric values, query double values, and we put the age and I put the ID in there as well. So if I get a query that says, find me documents where isHuman is defined and the age is greater than 48, we can construct this CQL query where we put both those terms into the where clause, push it down to the database and say, go and solve this problem. And that's a really easy thing for me to do. It's a harder thing for the database people to go and sort that out. But again, SAI is going to get better because a lot of the types of queries that you see coming from vector space are kind of filter using this metadata. Then do a vector similarity score. And then maybe I need to do some deduping and some ordering after that similarity because I've cut off the top 10. And I want to order those by some other thing. Complex queries like this, where you need to use ad hoc metadata to filter, are going to be more important over the next few years. Here's an example here with the subdocuments just to show that pathway. You can see where we've got address in the subdocument city. We do address.city. We put that into the map of all of the text values. And if I get a query that says, find me age greater than 48, address.city, again, I'm just constructing a SQL where clause and using the address.city as the path, putting it into the query text values. Okay, so the supershredding breaks it all down based on knowing the types of queries we want to serve. Then it puts a whole lot of pressure on the SAI to go and be able to serve those queries. Updating, what did we learn? We've got basic inserts and overwrites, and then all of our updates are read, modify, write. That's probably not true. I think you could look at an incoming request and say, does this require a read, modify, write operation? And then make a decision. But unfortunately, in Cassandra, if you want to go down the strong consistency, linearizable consistency path, you can't do it ad hoc. I can't say changes to this document are read, modify, write, so I'll do one thing and this one isn't, so I'll do something different. It doesn't work that way. So we're always going to have the document in memory, and we're going to override all the time. That tends to lead to better outcomes from compaction and from being able to, compaction has more work to do, but it's easier to drop stuff off because we don't have like one column written 6 months ago that has to sit way over in an old SS table and other things living at the front. So when we have an insert, we're just going to do the inserts. We saw those before, and then put if not exists on. And that runs a lightweight transaction. Currently in Cassandra 4, that's 4 round trips. It's faster in 4.1, and in Cassandra 5, that will be the same as a regular insert in the happy path. All right, now this really complex one, find one and update. This is all the things it can ask you to do, right? It can ask us to say, find something, but if you don't find the document, create the document, make the change, project it before and after. Basically, we have to pull this stuff into memory and make the change. They can't really get around it. So given a query that looks like this, we're going to update and, again, add the field and set the max. We're going to do a select. And we know that this query is by ID, so we're just going to get by ID here. We're going to deserialize that JSON, update it, and then redo the super shredding. And we fortunately have the maintainer and author of the Jackson library on our team. So when we want to make that go faster, we can. So that's kind of fun. And then we're going to rewrite everything with an update and see that transaction ID. If it hasn't changed from when we read it, we go back. This stinks. This is not great. It works. There's probably more elegant ways to do it once we have a better understanding, maybe if we move more things down to the database or something. From a Cassandra point of view, when 2015-16, we would talk about these things as something you shouldn't do a lot. And by this time and next year, when we have a cord everywhere, we're going to look at things like this and say, oh, this is just easy. Like, there's no reason not to do this. You can do this now. Okay, so what improvements did we come up with here? We've got a bunch of improvements coming to SAI for not contains on a set, not equals on map entries. You can see them all there. All support is coming. There's a CEP out there for not. I'm still a big believer and still push on global order by in SQL would be great. And limit and offset to be able to support those queries earlier. We've found some things we can improve in Paxos v1 without having to go to the next level. So what do we get out of all this? We can do successful just one-line config changes, and the Node.js app can come and work against DataStax Astra or Stargate sitting in front of Cassandra. Doesn't mean everyone's going to change this thing. What we wanted to do was make something that was appealing to Node.js developers. From a performance perspective, it's a difficult thing to get a handle on because we're doing things that Cassandra really hasn't liked to do in the past. But from a basic trying to compare apples to apples, just reading by ID adds about 0.3, 0.5 milliseconds to go through HTTP and the JSON stack and things. And there's still a lot more performance improvements we can put in there. Going to SAI, we've got a table with 3 million rows, and we go and do a read on one of those SAI indexes on the map. And 1.4 milliseconds read at the coordinator level to get through the rest of the stack, another 1.5 milliseconds. So SAI can deliver some performance. We also have an example of reading with 2 fields. Future, we've got more HTTP tuning to do because that's a new skill going up against native binary transport, which has years and years of becoming very good at being able to do high concurrency, high throughput. Maybe relax some of those consistency rules. We started this and in the before vector was such a big thing. With vector being such a big thing, you tend to have data that loads in as a bulk job or something like that, right? The embeddings are calculated, you want to push it in. Working out some way to deal better with that. All these SAI indexes, we're going to go and now work out how to deal with them all and make them more efficient. We've got a use case, so that's great. And just sort of more operations to support vectoring. If you want to get hands-on with this, you can go to Astra and get one of the vector-enabled DBs. There's a GitHub repo for this, Stargate/REST API, so you can stand this up against Cassandra. Sorry? JSON API. Typo. It says JSON API, sorry. And then also Jeff's doing a talk. Do I get a t-shirt for cocking up?
If there's any left.
Jeff's doing a talk about using this API now for things. And if you see this blog post about, building a Taylor Swift-enabled chat bot. So this happened in the last couple of days. There was a whole bunch of work put in to get this going quickly. And you can see an example on that blog post that came out this morning, an example of just being able to go, oh, look, I'm writing TypeScript, Node.js. I'm able to go and use Cassandra/DataStax Astra with all that power and do something really simple in Node.js, rather than have to get a driver and do stuff in SQL. So this example here is just searching on embeddings. So I have a couple of minutes for questions, if there's any. those T-shirts.
Here we have a question.
One at the back.
I don't need this thing. What's the most complex app that you've tested against this so far?
We've had some production apps test on it, like things that were originally coded to use another leading document database from another leading vendor that were originally coded for that, and so production things that other people have run. We launched private preview in September. Some of those SAI enhancements we've been able to do basic things like less than and greater than that are now available. Turns out there's a whole bunch of apps that don't use those. So the complexity will be, I think, in the vector space, right? So imagine at some point in the future, if someone wants to do this. I want to do a query of all of the restaurant reviews that Aaron's written that mention the word hamburger in them anywhere. I then want you to take that set of things and do a vector sort on it. And then I want you to sort them by the distance of what street corner I'm standing on. Those multi-stage queries will be the complex parts. Yeah.
Want a t-shirt, John?
All right, thanks everyone.
Okay. Hey, everyone. My name is David Polk. I'm a senior software engineer at Datadog, and I'm passionate about how Cassandra solves our big data problems. But recently, I've been curious about what Datadog can give back to Cassandra. So first, let me share a little bit about myself. I've always loved the water, from competitive swimming to scuba diving, and when the water turns to snow, skiing. During a college internship, I learned that aerial images could be used to map underwater forests, and clustering algorithms could be applied to quantify their degradation by human threats. Seeing how powerful the right pairing of data set and algorithm could be, I started my career developing machine learning platform at Amazon's Alexa. But one thing I noticed was that the iterations on the AI fundamentally depended on how efficient our platform was at processing the speech data set. So within a couple of years, I found myself fascinated with Cassandra because of how it enabled products to interact with huge data sets while providing high throughput. So how many of you here have experienced an outage and not immediately known the root cause? Okay, decent number of you. So you're not alone. The cause of a problem with Cassandra is not always immediately clear. Cassandra is complex. It's a distributed system that demands proper management of its resources, ranging from client connections across the cluster down to a node's heap memory. Understanding its resource management can be just as tricky. It requires knowing which cluster events are important, where are the logs related to those important events, how to monitor the metrics, and when to alarm in the monitors. There is so much data to process across the cluster, let alone a single node. When you encounter a problem, you usually need to start from a high-level symptom and drill down to the root cause. As Yuki mentioned in his open telemetry talk yesterday, this process can be time-consuming, tracking down app teams, trying to uncover relevant query information. Datadog can assemble data from logs and other metrics to provide context that is helpful in minimizing incident response time. So for example, instead of manually grepping through the GC logs for pause times, you could collect the metrics and extract their contents to Datadog. Or you could enable a Datadog integration, such as JMX, for other kinds of information. So if you're here, I'm going to assume you run some Cassandra in production. Let's say you're new to a team responsible for operating a Cassandra cluster. You don't know much about it yet, but you definitely want to make sure your cluster is healthy since it's on the critical path for your web app. Take a simple graph of request rate for the cluster. You can see that the cluster is servicing around 10,000 requests a second, has a cyclical traffic pattern. What kind of signal would you look for to determine if your cluster is not healthy? Well, here are 3 scenarios to walk you through what could happen. Let's say you're seeing a few sporadic timeout errors. And then one evening, you get an alert that a timeout's threshold has been breached. You acknowledge the page, get a cup of coffee, and start to troubleshoot. Since timeout errors can have different causes, how do you troubleshoot? Well, timeouts are triggered once latency is too high. So what does latency look like? You see that 2 days ago, latency was topping out around 60 milliseconds, and around the same time, the timeouts were pretty sparse. But once latency started to creep up above 100 milliseconds, that's when timeouts really started to explode. So why did latency start creeping up to begin with? You decide to look at one of the fundamental resources a node needs for answers. So high latency can occur when the node is strained for CPU resources. So what does CPU utilization look like? High CPU utilization. As the amount of CPU available decreased, the latency increased. So why the higher CPU utilization? A node naturally grows more strain for CPU resources as request traffic grows in the cluster. So what does request volume look like? Just as you suspected, more requests means fewer resources for each, means fewer cluster resources per each request. So let's provide more capacity to handle the extra requests. To provide more CPU headroom, you scale the cluster. Since the nodes also have little disk headroom, you decide to scale the cluster out rather than up. As you can see from the graphs, the new nodes come up on the top graph, the CPU saturation is alleviated, and the timeouts go away. What's your takeaway? CPU and timeouts are not linearly proportional. Once CPU is fully saturated, high latencies turn into timeouts, there are retries, and then you get a snowballing effect. So the rest of the week passes quietly, and you catch up on your sleep. But the next week, you get another alert that a timeouts threshold has been breached. You acknowledge the page, grab your cup of joe, and start again to troubleshoot. At first glance, you notice that the errors look a little bit more abrupt than last time. You pocket the information. Once again, you start by checking the CPU. You start to roll out the easy problems. Last time you had an issue, it was CPU saturation, but here, the CPU across the cluster looks pretty healthy. Even though you see a slight surge in CPU when the timeouts occurred, the nodes that timed out did not experience a CPU deficit beyond the other nodes. You think back to the abruptness you originally saw. What else can be abrupt? Garbage collection. So what is garbage collection? Memory management done by the JVM to remove unused objects from heap and free up memory. There are 3 types of garbage collection used by G1GC, a collector that we use for our Cassandra 3 clusters. First, there are minor collections. During these, the G1 operator will remove dead objects in young generations and move long-surviving objects to old generations. These collections stop the Java app briefly. Then second, there are mixed collections. During these, the G1 operator will find live objects in young regions while concurrently finding live objects in old regions, a search called concurrent marking. These can take a long time, but won't stop the Java heap. Third, the feared full collections. These occur because the Java app allocates too many objects that can't be reclaimed quickly enough. They stop the Java heap to clear the entire heap, or they stop the Java app to clear the entire heap, both young and old generations. So what about GC? Why would GC be relevant? As you know, the collections can pause the app, in this case, Cassandra. G1 tries to keep a pause target for collections. The limit is 200 milliseconds by default. But when a full collection is forced, the JVM must stop the application from running for a short time, during which Cassandra cannot service requests. So what do collection times look like for your cluster? So now that you see your garbage collection stats, you notice that before and after the timeout errors, the longest collection pause times were a lot shorter. But there were some times when the collection pause times went above 200 milliseconds. And as it turns out, these coincide with when you were seeing timeout errors. You don't have any direct signals here, but you're able to infer from the lack of CPU saturation and also the long-tail GC latencies that GC is not running smoothly. The timeouts correlated with the long pause times are enough of a signal for you to undertake GC log analysis. So when you look there, you see some detail about humongous objects. So what are those? Objects that take up more than half of a heap region are deemed humongous. The regions that consume these are automatically marked as old generation. You start to think about how these could affect collections. G1 can't collect a region without liveness information. During mixed collections, if concurrent marking that's supposed to attend to these old generations was not able to complete by the pause target, then these humongous objects remain in the old generation. And mixed collections require the concurrent mark to finish. So if G1 wasn't able to complete the mixed collections, could some of these old regions with humongous objects have been reclaimed again and again? And then you ask yourself, well, what would happen if many of your cluster's writes were deemed humongous objects? As the number of old regions grows, the number of free regions remaining on the heap would shrink. Pretty soon, there would be no more free regions left to utilize for the live objects in the young generations. Aha, and eventually the compounded allocation of many humongous objects would only be alleviated by a full collection, which would get triggered. To avoid this, mixed collections should ensure that concurrent marking completes. Giving concurrent marking more time to complete would be one way to fix this, but that would really just be a Band-Aid on the humongous objects problem. Instead, you could find a way to decrease the number of humongous objects and therefore the allocation rate into the old generation. So you read Oracle's docs, and you see that you should be picking a heap region size where the ratio between that and the heap region is approximately 248, while also being a power of 2. You see that you have a significantly smaller heap region size, confirming why you might have accumulated these humongous objects. So you increase the heap region size, deploy the update, wait for a few more collections to take place, and voila. You alleviated the G1 of instances where objects take over 50% of a region, in turn freeing up the heap of accumulated old gen, as you can see in the top graph. Your high long-tail GC latencies that trigger the timeouts have also disappeared, as you can see in the bottom graph. So now, but not least, a story about the graceful degradation of capability. So far, you've gained a better understanding of your cluster. And you come to understand the behavior of your GC. You've tuned its heap region size, so that now the collection times are much more reasonable, and you're getting better at recognizing CPU overutilization before timeouts start occurring. 1 month later, you see that CPU is sitting at an acceptable level at most times, but was abnormally high for a few brief periods. So if you look here, you see over on the left that during a roll and restart, the load in the cluster was almost flatlining. In the CPU saturation scenario, there was no real mystery as to why the CPU utilization was high. In that scenario, the query rate was also growing. At the same time, there was also a deficit of resources, so you follow protocol. First thought is to scale. So to add additional headroom, your two options are to either scale out and add more nodes or scale up the instance type. Vertically scaling is a relatively safe and normal operation. And you think you want to do that because you see that there is also around 5% disk utilization in the cluster, so vertically scaling would be a little less wasteful. So you run the vertical scale. The first node in the updated instance type comes up. It receives stream data from the other nodes. As it joins, it starts to serve CQL requests. Gossip settles. All the other nodes view the node as fully up. And oof, surge in errors. Like I said earlier, this cluster is on the critical path to your web application. During the operation, once the node joined, your web app started to experience an incredibly high error rate. You hurry to cancel the workflow and stop the operation, and after a couple minutes, the error rate subsides. Why then? Why did we start failing queries when the node joined? So what happened? The new node joins and starts servicing requests, and all of a sudden, all the nodes in the cluster have their CPU completely saturated. So how could the CPU get more exhausted after providing the cluster with more CPU resources? It's crystal clear that something interesting is going on here. Well, you see a 4x increase in request rate when you look at the request graph. The cluster is normally sitting around 10 to 15,000 reads per second, but after the node joined, you see a spike up to almost 30K reads per second. So you ask yourself, was this a retry storm? When the new node joined, the backlog of requests it started to serve could quickly overload the node. If those requests were pushed to other nodes, it could have overloaded them as well, leading to a retry storm. But then you look at the retry graphs and see that that wasn't the case. But then you look at this dark green line over here on the bottom graph, which represents a second type of query. They caught your eye since you started to see upwards of 10K of them as soon as the incident began. So you ask yourself, what are these other queries? You look at the request type, range slices. But what are range slices? Range slices are cross-partition queries. Here are a couple of examples where one is if there's no partition key in the where clause. Another would be if the in operator is used on a column which is a non-partition key. And also, range slices are typically expensive and, as a result, are a common cause of high latency timeouts. This aligns with what you just saw, a large spike in range slices along with an increased number of timeouts. So you wonder, where are the range slices coming from? You're tracking the queries with the app team's key spaces, and you see that there aren't any range slices there. So you wonder if the queries could be happening in the system-level key spaces, which you hadn't been tracking since they are typically uneventful. In this case, you dig up some more fine-grained metrics on requests. You end up finding that the driver was making a number of calls to the system tables without specifying a partition. So now you discovered the source of the range slice queries. But why would the driver need to make range slice queries? You look further and find that these range slices coincide with driver refresh periods. As it turns out, cluster-level information such as topology, schema, tokens, and status are held in the system-level key spaces, and the client driver queries these system tables for changes to that information. Why? It helps the driver gather information about the current state of the cluster so that it can efficiently route queries. Now what you're starting to think is, when you vertically scale, you perform a topology change. And when you perform a topology change, all the nodes announce to all the CQL clients, the topology has changed. I'm going to redo all these queries. So you saw that you could get a spike when you do a rolling restart of the client nodes. But what you didn't know is that when you restarted a single server, you could see a similar effect. So you took down things when you tried to vertically scale. You're probably thinking, the driver took down the cluster? What? Your company owns a number of Cassandra clusters, and you haven't seen this behavior before. So why is it happening to this degree, and why haven't you seen it before? So now you turn to client connections graph. The total number of connections on this cluster has grown to be very large. The top graph here shows the client connections. And what you're seeing is that the number of these connections has grown to over 60,000 per node. So why didn't we see this before? This is a huge number. Over the course of the past 6 months, the number of connections in the cluster has been steadily rising, increasing from 20,000 connections earlier in the year to its peak of 60,000 connections. So it's been kind of a slow climb. So what's causing this increase in connections? Well, like I mentioned earlier, the cluster is accessed by workers, and then the number of workers has grown, so hence their number of so has their number of connections to the cluster. So the driver is making these system-level queries when there are schema, status, or topology changes in the cluster. More specifically, range slice queries happen when the client is trying to connect to a host for the first time or reconnect to an existing host. So when the node went down, the cluster was perfectly fine. Each client received the down event and maybe tried to reconnect, but it stopped pretty quickly. However, when the new node joined and the cluster began to service TQL requests, every single client application began immediately performing range slice queries, interrogating the cluster for the most up-to-date information, which effectively DDoS the entire cluster and caused the outage. So in summary, range slice queries were triggered server-side, but the number of range slice queries that needed to be sent to an increasingly large number of clients. So how do we solve this? There are 2 ways to solve this problem. First is you could entirely disable the metadata queries within the cluster. The effect of this would be the loss of token-aware routing. Cassandra knows which nodes are responsible for which token ranges, and so it knows where to forward requests. In an application that values low latency queries, transmitting the information to the client is very valuable because it reduces the number of intranode requests to serve a single query. So maybe we don't want to disable it. Well, if we don't want to disable it, we need to try and control it. So there are a couple of refresh window settings which default to 0, and that results in the immediate request of information on status changes. By increasing that refresh window from 0 to, let's say, 5 minutes, each client will randomly be assigned some sleep period within that 5-minute window, and it'll wait for that amount of time before interrogating the cluster for updated information. So after applying a client-side change to this 5-minute refresh window, you can see here that this dark green line, which represents the range slice queries, has spread out because the number of client requests is spread out over that 5-minute window. And eventually, this will allow us to resume normal cluster operations and finally complete the scale up. So what are our takeaways here with these 3 stories? Well, the first takeaway is the importance of practicality for discovering metrics. Over the past 3 scenarios, you saw how you could dive into a particular problem, but it extrapolates more broadly. You saw a few request graphs across the 3 scenarios. The left column of graphs here is a slightly broader selection of request information, which is still only a subset of the request detail that we monitor. And then on the right side, you have another lower level signal that we use, disk usage. From these, we can answer important questions. Is a problem isolated to a single node, a replica set, a rack, a data center, or is it cluster-wide? Is a recent trend problematic, or is it only the peak of a cycle, such as compaction? If you were looking at the graph on disk, you might find that. And so many more. Having a breadth of information at your fingertips allows you to eliminate possibilities and quickly narrow the focus of what you have to investigate more deeply. And that allows you to move more quickly in a time-sensitive situation. OK, and here's a second key takeaway. When you have a lot of observability, it shows you a lot of interesting places that you can look deeper. Datadog provides you with the convenience of automatically strapping metrics. This enables you to navigate between correlated events, whether within a trace or across patterns that coincide. It also gives you more of a granular look at events. Otherwise, you might be limited to surface-level details. SSHing into a node and browsing through current JMX request counts or a few GC log files would not necessarily give you the full picture of what's under the hood. So up here in the top graph, you could see how you could take some errors and then automatically find the correlated metrics, the containers which are associated with those errors, and then let's say you pick a container. Well, then from there, you can see that container within the entire span of the containers or the nodes in your cluster, looking at all sorts of tag details on them. So my second takeaway for you is the importance of navigability. Ease of navigation gives you the ability to grow your understanding of the relevant metrics of your cluster from a small subset to a broader one, as well as how to monitor those for outliers. And that's all. Does anyone have any questions? OK, I think I see 2. Would you like to go first? Or either way?
Let me get you this way.
Thank you. It's been a while I worked with Datadog, but I remember you guys are very good with like helpful widgets and everything. I'm wondering if you have any kind of tooling or what's not to monitor client-side Cassandra matrix versus server-side, because there are scenarios where you can see a lot of timeouts on application side, but server looks healthy. That would be due to some configs. Unless you look at the throttling metrics, you wouldn't know that. So if you can tell more about it, that would be great.
Sure, yeah, absolutely. And that's a good question. It's something that over the time of us running clusters, we've gotten better at. We didn't start there, but it's definitely an important piece of observability to have, both client-side and server-side. And so where we've kind of come from is a place where we've had silos and 2 different, the application teams and then us having our own dashboards. And we've started to kind of bridge that difference by sharing dashboards around and kind of this. But then, on top of this, there are traces, right? So APM traces, and you can start from a query on the client side, and then you can drill into, well, how does that query break down? What are the different, time, like how long do the parts of that query take? And we're not quite there yet where we have a complete link from the client side to the server side for, let's say, a particular query where we can drill down. But that's definitely the direction that we're looking at and we're interested in going. So you can figure out, if some query you thought should not take that long is actually, maybe spanning multiple partitions or something like this.
Let me get you a microphone.
You mentioned that you have all these correlated metrics. How do you scale that? Because there could be thousands of metrics, and correlation is computational, fairly expensive. So you have all these correlated metrics, and then you know which ones are most suspect, and then you can start looking at that. That may give you clues of what's actually the root cause. Whereas in your example, when you went through that, you said the engineer noticed this dark green spot himself. He didn't really use your correlation.
Right.
Can you talk a little bit about that?
Yeah, sure. So I think this is kind of like where we were at versus where we're going. I picked some of these stories because they were interesting at the time for us, but then I guess looking back is 20/20 hindsight. So as time has gone on, we've come to recognize all the tools which are readily available to us, and we follow this process called dog fooding to try and make our own observability better by what's already available and what's becoming available. So correlated metrics is a perfect example of that. You might see some trends that follow the same kind of shape as the signals that you're seeing when it's like an error. But a starting point where we were at and we're kind of building from is just having a large dashboard of all these metrics which you are going to think, okay, well, in general, as you grow, you're understanding the cluster. This is what we tend to see is like, this is interesting and also this is interesting. So it's kind of more of a manual process at first, but then as time has gone on, we've recognized and started to take advantage of some of these more automated tools that, as you're absolutely correct, are important for making this robust.
Can you show that screen again? So yeah, right there.
Yep.
Yeah, right there. So how did you know that the current context is that orange one? Because you may have been working on another problem. How did it know to focus on that?
Oh, how did it know to focus on this specific?
How in that dark green spot that the network engineer knew versus what you guys found out from your correlation measure?
Yeah, so for example, you could look at this error, right? And you could see this is like a server-side, like on the server-side dashboard, the cluster's dashboard, this is some sort of timeout error. And then from there, you have the ability to navigate towards other kind of information with the same tags, so maybe like the containers which are associated with that error event. And then from there, you can move on over to there and say, okay, well, this is the container, and this is kind of where the manual step comes in, right? I mean, you could then look at that container from the perspective of the cluster that it's in and see, okay, is this error something which is limited, is it something that it has to do with a resource limitation or something like this? And maybe a helpful visual way of doing that would be to look at the entire scope of the cluster and to see, okay, like this is the node, this is the error. But in this particular case, this is kind of more just handcrafted together. So these are two disparate instances, as opposed to like one of the earlier scenarios where those actually were connected through step-by-step.
So is that correlation based on the Pearson correlation? So you have a time window of data, and then you do correlation between different metrics in the same time window. But what you're saying is something totally different. You're adding a lot more logic to look at textual data to see this correlation.
Textual data?
Yeah, like syslog. Am I understanding this correctly?
Yeah, well, I think with any sort of log or error or anything like this, you're going to be tagging it with all sorts of tags that kind of say that this event happened, on this service or on this machine or, like kind of during this event, maybe if you wanted to tag it in a certain.
If you put certain labels, then you're actually correlating the labels, not necessarily just doing a statistical.
Right, exactly. And the labels kind of you can think of can support that correlation. They can kind of lift it up on stilts and say, okay, like maybe there's some sort of trend, maybe there's a trend that happened completely across the company in a different application, but just because the shape of it is the same doesn't necessarily mean that it's caused by the same problem or something like this, right? So what you can use is tags to be like, okay, well, not only are these the same shape, but also these are closely related services. This is the client to that's like this service is the target, and this is the client, and so you can leverage that information to kind of tighten the confidence in that correlation.
Can I ask one more question? When you say you can, so are you actually using ML to do all these inferences, or this is something in the future? Or?
Yeah, yeah. So, I mean, yeah, this is all kind of in its own separate group within the company, but yes, there's right. So there's all sorts of things, related to ML forecasting of, trends. Is this more of a seasonal or cyclical trend, or is this a permanent direction that we're going in? And then in this case, though, yeah, like figuring out the correlations of events, statistically based. Yeah, so in fact, if I were to, and I didn't have this on the slide, but if I were to click on, view the correlated events, you would see a drop down of a bunch of other events that maybe are errors on different services or something like this that occur around the same time, or maybe they have the same shape, or maybe they have a lot of the same tags, but these are the things, and then of course they're ranked based off of some sort of similarity heuristic. Huh? Maybe after. One more?
So in Cassandra, is there any metrics that we can monitor or see the network issues? Or?
Yeah, absolutely. So that's another panel that we have on our dashboards that I didn't show there, but absolutely. If you have some sort of network partition that is preventing some of your nodes from connecting with each other, that would show up on some of our dashboard graphs that are related to ingress, egress, all sorts of network data. Yeah. Oh, okay, yeah. So yeah, everything comes through ultimately the Datadog agent, which is configured to just basically streamline metrics across different feeds, JMX being one of them. So it might listen in on JMX, but then some other things as well.
Where do these agents run?
Sorry?
Where do these Datadog agents run? On the Linux box, or do they actually run in the target VM?
Yeah, so these run as a container alongside.
Okay.
Yeah.
Your target managed object that you're trying to launch.
Yeah. Well, I think I'm just about out of time, but thank you for attending. If you want to chat more, feel free to reach out to me. Yeah. Sure, yeah.
Yeah, I'd like to link in with you as well. We leverage Datadog very heavily at Samsung Smart Things. We have a lot of
Test 1 2. Test 1 2. All right. All right, welcome everyone. Hello, I'm Philip Moore. I'm from Voltron Data. I was going to be co-presenting this session with Sebastian Estevez from DataStax. Sebastian just had a little baby girl, so he wasn't able to make it, so I'll do my best to do it on my own. Please forgive anything I miss, but I'll do my best. So this session is how to do OLAP on your Cassandra data with Arrow, Flight SQL, ADBC, and DuckDB. So we'll be talking about these technologies, how they all fit together to allow you to do OLAP queries on your NoSQL Cassandra database, including AstraDB, of course, DataStax's commercial offering of Cassandra. So DataStax and Voltron Data, we kind of teamed up and we built a Flight SQL server for an Arrow native engine to enable OLAP capabilities for AstraDB or Cassandra. So if you had not heard of Flight SQL, it's relatively new. It's part of the Apache Arrow project. It basically lets you connect a server up to a data engine that is really, a data engine can really excel at querying data, but may not be necessarily interested in presenting a server to allow client connectivity. Flight SQL kind of lets you complete that picture and lets you enable that client connectivity to your data engine. So think of it as a component in a composable data system. So at Voltron Data, we really believe, we're big believers in the composable data systems. So we do that by establishing standards. So we have a substrate, which is a representation of a query plan. It's a machine representation that should be universal and can be sent to various data engines, including DuckDB, an engine that we've just announced called Theseus that's used a GPU. I'll talk about that a little bit. And we have ADBC, which is Arrow Database Connectivity. And the really cool thing about ADBC, you've probably heard of JDBC and ODBC drivers. ADBC takes it a step further and allows columnar data exchange throughout the entire communication process. So if you're familiar with even columnar databases like DuckDB or Snowflake or whatever, usually at the last leg of the trip, they have to transpose the data to row-based format before it gets to the client. Arrow changes that, and Apache Arrow format is columnar. So that means that the data is coming in a columnar format all the way through to the client. So it's an optimal transmission method for the data. So I just touched on Arrow being a columnar data format. So formats like Parquet work really well with Arrow because it's already a columnar format. But Arrow just enables that columnar transfer. So if you're not familiar with columnar data, it's really easily compressed, much better than a row-based format. So it's much better for OLAP queries, and it works really well with vector databases that process vectors with one single instruction. They can process multiple rows of data. So we enable a user interface via ADBC. We also have an Arrow JDBC driver and an ODBC driver. Now, the JDBC and the ODBC, the data comes in a row-based format at the last second. It gets transposed. So it's not as good as the ADBC driver, but it lets you get to your Arrow data Flight SQL server. We, of course, have execution engines. In this case, in this demo, I'll be showing DuckDB. DuckDB, if you're not familiar, is an in-process database, a data engine. It's really, really good at OLAP queries. It's free, it's open source, and it performs really well on AWS Graviton or even x86. So we'll be kind of showcasing that a little bit. And we believe in open data storage formats like Parquet and ORC that allow you to talk to you can talk to your data with various engines if you use those open formats like Parquet. All right, so I'll kind of get into the solution architecture, what we built here. So the first thing, of course, Cassandra is a NoSQL database, like an object store, but sort of. And it's not really, it doesn't lend itself well to OLAP queries, like things like joins and things like that you typically do in OLAP type queries. If you're familiar with data warehousing, you know that typically you have a star schema, a fact table that you join to dimension tables via a dimension key. And those types of things don't work well in CSQL or CQL, sorry. It's not designed for that purpose. So we have to export the data from Cassandra to an open format. We happen to choose Parquet. So Seb and the team at Voltron built this near real-time export process. So it makes the Cassandra data available as Parquet files for analytic engines like DuckDB or Theseus. Separate analytics infrastructure with zero impact on Cassandra latencies. It doesn't go through C-SQL, so this is like a separate process. It handles tombstones deduplication. The tombstones deduplication happen on the OLAP engine, so this thing is kind of pretty lightweight. It doesn't have to handle those types of things. This proof of concept that we built uses a repo that Seb, I think, created. It's a DataStax SS table to Arrow. And it just basically lets you export your data from Cassandra to the Arrow to format. So you can see the snapshots or backups happen in near real time, and it goes from the SS table format to a Parquet. Now, when the Parquet files that get dumped out, we upload them to like an object store like S3 or GCS, Google Cloud Storage. All right, so once you've exported the data, now you need to be able to query it, of course, right? So you need a data engine that's really good at OLAP. So for this proof of concept, we use DuckDB. And the really cool thing about DuckDB is it speaks Arrow very, very well. So it talks to the Arrow ADBC and JDBC drivers in the Arrow format, which is columnar. So the way the flow works, there's kind of two avenues to get to the data. If you remember, I mentioned JDBC and ADBC. So a typical SQL client is usually ADBC or JDBC or ODBC. So they will issue SQL to the JDBC driver, which then sends the SQL down to the Arrow Flight SQL server process. This then sends the SQL to the data engine, which in this case is DuckDB. Hopefully it's Voltron Data Theseus in the future. It uses GPUs for acceleration. The data engine, of course, talks to the Parquet format. Now that could be on local storage on the actual Flight SQL server local file system, or it can be an S3 remote file system. It doesn't matter. Now, there are performance implications, like if the local file system is NVMe, solid state, and all that stuff, it's going to be probably faster. It's going to execute more swiftly because the data is local, it doesn't have to go through the network to get it. So once the DuckDB engine gets the data, it processes the query, and it sends Arrow data to the Flight SQL server, which then sends Arrow data to the Arrow Flight SQL JDBC or ODBC drivers. And at that point, the driver has to transpose the data to a row-based format for the client. So that last leg of the journey is not as optimal as it could be. That's where ADBC comes in. So ADBC, it's very similar to the route I just explained, except that you're sending SQL through and you're getting Arrow data back at all legs of the journey here. So it's a little bit more optimized for that high data transfer. So if you're querying millions of rows of data, you're going to see a big bump by going to ADBC. Now, if you're just querying 5 rows of data or 1 row of data, the difference is so negligible that it's not a big deal. All right. So as always, there's always a trade-off. ADBC is very new, so not a lot of tools adopt it yet. But there's a lot of tools that talk JDBC. So you're probably going to use JDBC for compatibility, but if you need every drop of performance, you probably want to go to ADBC. So that's kind of how the architecture works, or the solution. Now let's talk about the architecture. How do we actually implement this thing? So we deployed this proof of concept in Kubernetes, and we used AWS Cloud for this. There's nothing stopping you from doing this in GCP or Azure. It's just the cloud we chose. So we run a stateful set in Kubernetes here that has the Arrow Flight SQL server running and DuckDB, of course. We have 2 avenues for the data. So we attach a local NVMe drive to the instance, but we also have access to S3. So it just allows you 2 avenues to get to your data. If you want, remember there's always a trade-off, as you guys know in IT. If your exporting process is writing to S3, it's always going to be up to date if you're querying S3. But if you're going to be querying your local storage for performance, you're going to have a synchronization process that copies the data periodically from S3 to your local drive. Sorry. All right, so the other cool thing is that we are using Graviton. So DuckDB runs really, really well on Graviton. So we're using Graviton 3 instances. And these nodes can be pretty beefy. So we're using R7GD 16 extra large, which has, pardon me, 64 CPUs and 512 gigs of RAM. So it's a pretty beefy server and actually gives you really good performance that's comparable to things like Snowflake and Databricks SQL with terabyte and below workloads. So you can't go too big with this. You can't query like a 10 terabyte database. You can, it just won't perform as well as like a commercial solution. But it's really good for the money, which is very cheap. So these instances, I think, cost like $4.50 an hour. So to run terabyte scale analytics for $4.50 an hour is really good. And again, so the Arrow Flight SQL ADBC or JDBC client is just sending queried through a load balancer, which has TLS. So all the communications are encrypted, and of course we enforce authentication so that we don't want to just let any schmo get in and get our data. But if you're familiar with DuckDB, there is no authentication. So we actually, the Arrow Flight SQL server adds a value layer there it's enforcing authentication and encrypting the traffic to and from the database. So it's a secure solution. All right, so I'll try to demo the solution here. Please pardon me. All right, so I'm going to use one of my favorite tools, dbeaver here. So I think they're one of the sponsors of the event. And I talked to them upstairs, got a sticker, so I'm really proud of that. I've gone ahead and instantiated connection. So I'm running a Flight SQL server now in AWS, in Graviton. This is a live demo, what could go wrong? And it's running that R7 16 GD extra large. So it's got that local NVMe, 64 CPUs, and 512 gigs of RAM. So if I have to instantiate a connection here, and it did, I'm running 092 of DuckDB. I think that's the latest version as of an hour ago. Hope they may have released since then, who knows. And if we query the DuckDB settings table, bear with me here. You can see that we've given it 425 gigabytes of memory. So we didn't give it all the memory on the instance, but that's a lot of memory. And we, I think the threads parameter is so we give it 60 CPU threads. So it's pretty beefy in terms of a database, much bigger than you would think you could get available for free. All right, so we've registered some views here. If you expand here, you can expand your views here. And so we don't have any tables in this database. We have views on top of Parquet. So the cool thing about DuckDB is you can create a view and just select directly from the Parquet. You don't have to ingest the data. It's actually faster to query Parquet, ironically, than the DuckDB internal format, because the DuckDB internal format is designed for updates and things like that. Parquet is not really designed for that. So we've got basically two versions of the TPCH schema here. One that's on local NVMe, and then the other is on S3. So if I query the customer table, it's going to go from the local disk. If I query the S3, it's going to read from S3 live. So let's test that out. Moment of truth. So you can see I query the region S3 table, and it just pulled directly from the S3 bucket. You have to trust me that it worked, and so forth. And you can run longer queries, like I can sum the extended price and get a record count. I won't run this one because it takes a while, but if I run the other version here, you'll see the latency is a little bit better, right? Now, how much data are we dealing with here? So this is TPCH scale factor 1000, so it's a terabyte scale. So if I run this query, you can see that's 6 billion rows of data it just counted. And sum that extended price, which is very high. But so it queried 6 billion rows that fast in the Parquet. Now it cheats with Parquet. There's some information in the Parquet that lets it cheat a little bit, but this query is a little bit harder to cheat with because it's querying all these attributes. So we're going to query the line item table and filter on the ship date and do a group by and order by. And so this query will execute a little while. Talk amongst yourselves. All right, it almost always takes 10 seconds, so It's like Old Faithful. As it only produces 4 rows of output, but it actually queried 6 billion rows to generate those 4-row totals. All right. So to me, like that blows my mind because I came from the Oracle world, and to get that type of performance on terabyte scale, you had to spend a lot of money with Oracle. So it's very exciting to me to be able to see this an open source solution running on Graviton with ARM processors for $4.50 an hour run that fast. Like it really blows my mind. I'm excited about it. So, so pardon, I'm nerding out a little bit. I apologize. But and then we can run query too. So you can, if you're familiar with the TPCH query suite, there's 22 queries that you run to see kind of get a general feel for performance of the database. So I don't don't remember how long this one runs, but it shouldn't take too long, hopefully. Yeah, so 5, 6 seconds, something like that. So as you can see, DuckDB is really performant. And the cool thing about the Flight SQL Server is if we find something faster and if it speaks Arrow, we can swap out DuckDB for that new thing. So it's really good for the champion challenger model. You can swap out components as new components that are shinier, faster, better become available. All right. So all this cool stuff is open source, of course. So we're standing on the shoulders of giants. So Voltron Data has a repo for the Flight SQL Server portion. So it's a public repo. If you do me a favor, star it, that'd be awesome. But it's the Flight SQL Server example. And there's this awful guy named Philip Moore that works on it, but that's me. But long story short, in the README we show, hey, how do you run this stuff? So it's easy to run in Docker. So you can literally copy that, start a terminal, and spin up a Flight SQL Server on your laptop just like that. So if I do a Docker PS, let me make sure it's running. There it is. So I'll do Docker logs, Flight SQL -f. All right, so it should be listening. So instead of the AWS one, I'll just connect to localhost, hopefully. And in this one, we actually do have real tables. So if I open a console, I didn't generate a terabyte of data on my laptop, by the way. So if I do account star of this line item table, so it's 60,000 rows, much less data. So, but I have run 10 terabyte scale on this. It's not as nearly as zippy as terabyte scale in AWS, of course, and on the laptop. So it's probably not a good solution if you're trying to query 60 billion rows. But if you're at that terabyte scale or below, it's a pretty good solution, I think. Now, the other things to worry about are concurrency. The solution, DuckDB doesn't really like multiple users connecting at the same time. It's not designed for that. So if you try to run 2 queries in the same database at the same time, it's like crossing the streams. Bad things can happen if you're familiar with I'm old, sorry, it's a Ghostbusters thing. But so you can get some strange errors if you try to do concurrent things with DuckDB. Now, we have mitigated that in the past in the Arrow Flight SQL Server code base, which is a C++ code base. You could put things like mutexes in that, basically lock a resource, you query some stuff, and then you release the lock, and then the other session, they just block and wait until that mutex is released, and then they're able to query the database. So that's something that's not ideal. Obviously, a more commercial solution like Snowflake or Oracle, they're going to handle concurrency much better than DuckDB would, because they're designed for that. Cool things so this is a JDBC driver, of course, and then the repo, there are instructions on how to download and set up the JDBC driver. So we have a link to another repo that how to set up the JDBC driver in dbeaver. So it just takes you to the screenshot step by step. Hey, if I want to start messing with the Flight SQL Server, how do I get started? This is a good way to get started and just query the Flight SQL Server and turn some really wicked, crazy queries against it. Of course, there are links also to what's Apache Arrow, and talks about Flight SQL and Arrow and all that good stuff. So there's some article, blog links and things like that. And of course, we say, hey, if you just want to mess with DuckDB directly, you can click on the links to go to DuckDB. So there's also a section here where you can start up. This is an example where you can attach your own database, and you can. In this example, we generate a 1 gigabyte scale factor TPCH database, and we start the Docker container mounting that local database file. So you can get an idea. That's going to be, I think, 6 million rows as opposed to 60,000. So the 60,000 is very small, of course, but you can start playing with bigger data sets on your laptop. You don't want to get too big. You know, don't want to go a terabyte because you probably don't have that much storage local. And if you did, you probably don't want to fill it up with a database. So the other cool thing is we do talk about how to set up the JDBC driver, but we also talk about how to connect and run the ADBC Python Flight SQL driver. So if you follow these instructions, you can, we'll try it here, we'll try it live, Bill O'Reilly style. So we'll just, we'll go ahead and set up a Python virtual environment and install the packages. All right, and then, so this is a little snippet of code here, should connect to the Flight SQL database that's running locally on my laptop and just run a query. So this will use that optimized ADBC driver and get columnar data all the way through. So if we, hey, it worked, all right, wow, thank God. All right, so as you can see, it just returned, I just selected from nation, where the nation key is equal to 24, and that happens to be the United States. That one record out of the nation table. This format might look a little bit weird because it's the pi-arrow format. You're probably used to pandas. Pandas is row-based, and pi-arrow is, of course, columnar data. So each column is represented with an array as opposed to a row-based format. So that's why it looks a little bit different. Now you could, of course, do a 2 pandas on that. So if we do a x.2 pandas, it looks on that row-based format. So Arrow works really well with pandas. You've probably heard of pandas, of course. Wes McKinney was a co-founder of Voltron Data. He's moved on now, but he made sure that pi-arrow really worked well with pandas. So that's about it for the presentation and the demo. I'm glad to take questions if you'd like. Okay, so let me get you the mic. I think they want to have everyone. Thank you.
So when you copy the SS table to to your destination, right?
Mm-hmm.
You mentioned, well, there's duplication of data there. I said that, okay, so the OLAP portion is going to take care of it. Can you elaborate on that? Is that when you run your query, that's going to take care of those duplicate, or is all those duplicates going to be, well, still duplicate in the destination?
Yeah, that's a really good question. So in the way we handled that, and I didn't actually demo that part, I apologize because Seb wasn't here, but we actually create views on top of the SS table export data, and we do a max by. So there's some timestamps that are generated for each column, that basically like a version history of each column of the SS table. And we select the value that has the greatest timestamp. So we create these views that have that max by operator. So it lets you get the maximum value by another value in the table. And so that effectively that takes care of the tombstones and makes sure you have the latest version of that data. Now there's a performance penalty because you're reading more data than you would have to if you just had the latest version. But it's still functional and works pretty well.
Okay, well, tombstone and latest is one thing, right? But you got if you're using a replication factor of 3, you've got 3 copies of the data there, right? So your 6 billion row that you mentioned earlier originally was only 2 billion row, right?
And in this case, this was TPCH, so this was an OLAP data set, so it wasn't even an SS table. But so Seb actually has the process generate the SS tables. I don't have that part of the solution. He was going to demo that part. But
Got it, okay.
yeah, so I was querying regular generic data, but essentially it's the same kind of thing.
Got it, thank you.
Yep, thanks.
I was just going to say, if that view is taking the latest timestamp for each cell, it's probably just taking a distinct. So that the
Yes.
distinct
Okay.
already.
But your OLAP database still have 3 copy of the data still.
Underneath the view, yes.
Okay.
Yeah, and there is a penalty for that. So it's not going to be as fast as if you just had the latest version.
Did you compare the performance with other OLAP solutions like ClickHouse?
Oh, that's a good question. Now, I haven't done ClickHouse. I have kind of benchmarked against like Snowflake and Databricks SQL. They're faster, of course, but they're way more expensive. But I haven't done ClickHouse. I need to do that. So that'd be really interesting to try.
And also, was this a prototype or was it powering like a client-facing application?
It's just a prototype right now. I think Seb is going to roll it out a little bit soon, but I'm not. Don't quote me on that. I don't know.
If you had multiple servers that had DuckDB running on them, do you have any idea how you would keep consistency with the local files, so that if you're writing to one of the nodes that you get the same data? Or just asking in the...
Yeah, that's a good question. I think if you have them all query the S3 live, that would maintain some sort of reasonable consistency. But if you copy...
Cost,
yeah, exactly, yeah. I haven't done that, though, so I'm hesitant to say that works great because like there could be some concurrency cost or some locking that I'm not aware of that could happen. But I would be me to try, yeah.
When you export data to Parquet, do you have any kind of options to partition a certain way? Because like all of the things when you do in Parquet, it practically depends how you partition it.
Yeah, I'm not...
So is it faithful export of SS table? It's probably just brute force.
I think it's just brute force now, but of course it is open source, so you can change the code to partition the way you want it to. I think. I don't want to speak
it's
for
a little
Seb.
bit like, okay.
Yeah. I think we have a question back there.
Hey, thanks. I was curious about, it seemed like a core part of this was this kind of like keeping a columnar on the wire all the way up to the client, like the ADVC. Like, is that actually significantly better than just doing some form of like compression of row-based, like some form of like dynamic LC4 on top of that? Is this like significantly lower total bandwidth back to the client? And if so, like what kind of ratios are you seeing?
I've seen 10 to 1 on big data sets because like particularly it all depends on how much repetition you have in the column.
Right.
And row-based data compresses pretty well too if you have a lot of repetition. But since it's columnar, like say you have a very low cardinality column like that has 2 values,
right,
and you got millions and millions of rows, that's going to compress really well in a columnar solution. So we have seen 10 to 1. But now if it's 2 rows of data, it's not going to be measurable. You'd have to be really fast to measure it.
Yeah, I was just curious relative to like generic kind of like if you have a page and then you just run a good compression algorithm that on like LC4 or something, like you also get ratio. And I'm just curious, like, is the columnar format really coming out ahead there? And I guess it sounds like the answer is yes.
Yeah, from what we've seen, yes.
Sorry. I Yeah, I understand the advantage on the storage engine side. Okay, thanks.
The other thing is there's a serialization and deserialization cost. The cool thing about the Arrow format is you minimize deserialization and serialization. Because like it's shipped in the same format all the way through this ecosystem, if that makes sense. Other databases typically have to do some sort of translation for the client to understand it, I guess. So like an Oracle JDBC driver, for example, is going to get it over in the Oracle wire format, but then has to transpose it or deserialize it to present to the client, for example.
I see. So you're saying that internally Arrow is, even though it's presenting it as like a list of integers, it's actually only storing that once internally. That's what you're saying.
Yeah. Essentially, it's some sort of magic that's happened. I can't explain it 100% faithfully, but like,
gotcha.
It minimizes serialization and deserialization, and it's the same in all languages, all formats. So like, it's the same in Java as it would be in Python and so forth.
Right. That's very interesting. Thank you.
Thanks. Any other questions? All right, I think we're good. Thank you. Thank you, I appreciate it. Thanks for coming.
1, 2.
Test, test.
Tail of the dragon yourself? Tail of the dragon?
Okay. So welcome everybody. Today we are going to tell you how we operate Cassandra over Kubernetes with Temple. Just before we start, does anybody operate Cassandra over Kubernetes in the audience? Yes. Okay, cool. Well, hope we'll give you incentive to do that. So a word about us. We're working at Datadog. If you don't know us, our company is providing observability as a service. At scale, I guess our flagship product historically has been collecting metrics and showing dashboards, but today we have many more things, alerts, APM, synthetics, security. My name is Christian. I'm working as a senior software engineer at Datadog. And my first encounter with Cassandra was in 2016, I think. Small cluster, 3 nodes. Things have changed here since. And when I'm not on computers, I run. Went for a run yesterday, went for a run today, we'll go for a run tomorrow, you get the idea. And Steve, my coworker, senior software engineer as well, is the team lead of our Cassandra team, which is composed about roughly 6 engineers, like 6 exactly at this time. So what are we going to talk about? First, explain you a bit what Temple is and why it's a great fit for us. And then we'll dive into 2 very concrete examples, get our hands dirty on the health check team and migrations. Here we are talking about moving data from one place to the other, not schema migrations, so that kind of migrations. And then we'll give you an idea of what's our future. What problem are we trying to solve? Of course, we run 24 hours a day. You possibly do the same. For us, it's really critical. I've been several companies, but Datadog, people rely on us to just know if anything goes wrong. So we have to be more reliable than our customers, long story made short. We run hundreds of clusters, thousands of nodes. Numbers are changing, but that's fairly big. And one thing, since we are full Kubernetes in the company, Kubernetes came after Cassandra, and its design makes assumptions that are not that Kubernetes friendly. So you have to just navigate through this, and it gets a little complicated. Also, our infrastructure is always changing. When I joined the company, it was just virtual machines all over the place, only one cloud provider. Now we have multiple cloud providers, we're full Kubernetes. And even within the Kubernetes world, we've been through different ways of using it, and you have to adapt your thing, move it from one place to the other, just deal with the computing world is ever always changing. And also, our team is not that big, and we're span on different time zones, so this has an impact on operations. So what is Temple? I got that from the Temple website. That looks great. It's going to simplify your code, make your applications more reliable and everything. You want that. But what is Temple exactly? Let's just dive back into ops. In the beginning, I guess everybody is doing that simple thing of running shell script, like not even shell script, like bash commands. You read this tutorial on how to do this or that with Cassandra. You just shoot some commands and do things, and that's what you do initially. And then at some point, as you organize yourself, you kind of document this because you don't want your coworkers to rerun, hit the same walls you've been hitting. So you just document the process. And you get a run book that tells you to do this, do that. And at some point, you figure out, well, those engineers, they're just doing this sequentially. Why don't you write a script that does this automatically? And so, you turn the road book into some kind of script that does the thing, has been hopefully tested a little bit. And then you can go one step further and have your scripts be orchestrated, organized. I'm naming a few tools that allow you to do that, Chef, Ansible, whatever. Basically, you have this thing under control, and you know that whenever you deploy something, a bunch of things are going to happen, and you get the thing under control. And then Kubernetes takes it a step further. You just describe, hey, I want this state. I want these things. Please do the magic behind the scenes and converge to that state I want, and it's just going to run all the commands that are needed. So why would we need Temple? Temple actually is a workflow engine. Think of a workflow as a script on steroids. It's really a sequence, a program, a sequence of actions that it's running, and Temple is going to orchestrate that. Why is that important? We'll see that later in detail, but it allows you to typically know what's running, at which state is it. It's going to retry things. It provides you a single pane of glass of whatever is happening in your infrastructure. And it's a great addition to all the other things, like all these 5 things, runbooks, bash scripts, bash commands, tools that bundle them together, or Kubernetes, they all coexist together. It's not like one is replacing the other. A pattern that we used a lot on Kubernetes is the toolbox. This thing is kind of the old world of virtual machines making its way to Kubernetes. It's not really Kubernetes-ish. You are not recommended to do that, but it's really efficient. It's like almost it feels like you're SSHing on your server or your infrastructure, and you have this side thing where you can run commands. And on our toolbox, typically we have commands like this rolling cleanup, which is doing exactly what it is written on the tin. It's just a cleanup on all the nodes, and a bunch of other commands. And that's a useful pattern that we still have today. And let me describe you a little bit our temple setup. So we have this orange zone with the temple server. So that's just the headquarters of Temple. So you have this application running. And then it delegates the execution of scripts of workflows to the Temple workers. So here we have 2 different workers. They are each color represents a Kubernetes cluster. And worker blue is going to operate on these Cassandra X and Y, and worker green, or light blue is going to operate on the other ones. And Temple does the work of dispatching things in that place, in that place. It does the magic behind the scenes. And you'll notice one thing is that there's a Cassandra that is operated by Temple, and that powers Temple. So when you operate on that cluster, you just pay attention, because you could break things. But we'll always be fine. Here are a few random names of our workflows. They're self-explanatory: deployment, health, cleanup, list stop pods, replace nodes, rebuild nodes. We do pretty much everything with them. So now, one thing, the health check. That has been a really important building block for us. It's just about answering this simple question: is my cluster OK? And that is not something that is like either totally OK or totally broken if you've been working with Cassandra. So there's this thing that from the Kubernetes point of view, it's going to be, it's OK if all my pods are just ready and have their readiness check OK. From the Cassandra point of view, node tool status is going to tell you those nodes are up and working, those nodes are not, and depending on which Cassandra node you're asking, you'll have a possibly different answer. On the 4-node cluster, it's rare, but on the 200 nodes cluster, well, your management may vary. And then there are monitors. We're like a monitoring company, and at some point, maybe your node is at 99% CPU. Maybe it's at 98% disk usage. It's not OK. You may not proceed. So it depends. So yeah, this thing has been really a very useful building block. We use it pretty much for everything: deployments, node replacements, migrations. And one thing that is really important is that by building this block, it helped us enforce good practices. And things went much more reliable once we had something that was like reliably telling us, hey, you can move forward. And that is possibly the most important slide I'm going to talk about. I'm going to move a little bit because I need to show things. This in the Temple world is an activity, this purple block. Purple blocks are activities, and they are retryable chunks, something that Temple is going to retry if anything fails. And inside are just function calls, and one block like this is a workflow. So let's take workflow 1. You run your thing, you do a health check. The check is OK, so you proceed to A. A fails. Oh, that's too bad. Then you retry the whole activity. And then so you retry, check OK. Now A is OK, B is OK. Proceed, go to activity 2. Now the check fails. And this is usually typically fatal. If the check fails, you just stop everything. That means the cluster is not healthy. I'm not moving forward. I'm not retrying anything. The other example on the right, I'm not going to detail it, but the semantics is different. There's only one check. So you could end in this situation at the end where C is being retried, there's been no check before it, and we tend to prefer the first option on the left, but it does have a cost because the check itself can be lengthy because imagine it's going to do in some variants like a no-tool status, the equivalent of no-tool status on all the nodes. So you have a big cluster, it's going to be lots of calls. It could be up to 10 minutes or something. Do you want your workflow to wait 10 minutes each time? That's a design question. But I think we really made great progress being forced to ask us all these questions. And now most of our operations are like more reliable. To sum up, a health check looks really simple. You're just like, does it work? Does it not work? But you have to dive into the details. And I'm going to let Steve talk about another use case.
Thank you, Christian. Hey everyone, I'm Steve. I'm going to be talking about another use case of ours for temporal, which is migrations. So health checks are kind of the building blocks, but this workflow is going to be a little bit more complex and a lot more moving parts. But with the continuous evolution in technology, infrastructure migrations are inevitable as teams constantly try to improve performance, scalability, and reliability within their systems. In the time I've been here, we've undergone a number of these migrations. We've transitioned our Cassandra infrastructure from a non-Kubernetes environment to a Kubernetes environment. We've migrated Cassandra clusters across Kubernetes clusters, and we've migrated our Cassandra clusters from our initial K8s config to an operator ecosystem. All of these migrations involve a large number of engineering hours with incredibly high stakes, as we're moving massive amounts of data that are critical to our product and our customers. And it's really difficult. There are many, many steps involved. Health and safety checks are required. Actions need to be repeatable and reliable. And as Christian mentioned earlier, with the evolution of operations, temporal solves a lot of these problems for us. So let's dive a little deeper into the progression of our migration between Kubernetes clusters and how it evolved over time. So we designed the workflow with 3 things in mind. It needed to be robust. It was going to run for all of our Cassandra clusters, varying both node count and density across multiple data centers, multiple cloud provider regions. It was going to move massive amounts of data, and we needed to have the utmost confidence in the automated operations that would be executed by temporal. It needed to be pragmatic. It was OK for us if it wasn't just a single button press. Although that'd be great, having pausing points in between would give us and the application team a chance to assess progress and verify that there haven't been any lapses in performance. But we did want to automate the boring parts. Streaming operations between nodes take many hours, depending on cluster size, density, and we didn't want an engineer to have to sit there and monitor constantly for completion. Lastly, we didn't want to waste resources and double the cost of our cluster by standing up an entirely new cluster and doing a rebuild from there. We also wanted to design it with making it incremental. We knew the workflow wouldn't be a complete product from the start, but it would help us achieve our goal in the short term, and we would build it with reusable and adaptable components like the health check. So the core logic was converted from an initial migration that we'd used previously, but as it developed and we encountered more nuanced situations, features were added, such as being able to pause and resume at different points in the workflow. So if we look at what the typical timeline would look like manually, in practice what we wanted to do was a series of node replacements where the old node was in the source Kubernetes cluster and the new node was in the destination Kubernetes cluster. So thinking of how this would work with manual operations, the timeline would look like this. We prepare node 1, we perform a cluster-wide health check, we'd stop the previous node, we'd prepare the new node for the replacement, we'd start up the node, and we'd let the replica stream in all the data, and wait a long time. Start for the next node, and the next node, until all the nodes had been converted from the source cluster to the new cluster. So there's an obvious pattern here, and we knew that streaming would take the majority of the time. If we were to do this manually, there would be constant changing of context as we look to see if the streaming has completed and we can move on to the next node. This was the perfect situation for temporal, which could start the next node replacement as soon as the previous node was finished and sufficient health checks were completed. So here's a simplified diagram of what this migration would look like in a K8s environment. This is a Cassandra cluster composed of a single stateful set striped across AZs for high availability. This means that nodes migrated to the new Kubernetes cluster are going to be housed in a separate stateful set on the right. But we need to ensure that data is kept consistent across racks and availability zones. Therefore, we need to be a little bit more careful than simply scaling up the new stateful set and scaling down the other stateful set. So instead, we need to work in batches of 3 and slowly decrease the size of the source stateful set to reduce the risk of being in an unhealthy state. So on the left here, pods 3, 4, and 5 have already been migrated and correspond to ordinals 0, 1, and 2 on the right. To add ordinal 3, we needed to replace pod 0 since it's in the same AZ and let the cluster stream in the replicated data. We can't just scale down the stateful set at that point because that would delete pod 2, which still is an active replica. So all these steps that I just described needed to be implemented in our workflow for it to be successful, which meant deciding which of these actions were retriable, interacting not only with Cassandra, but with the Kubernetes API, understanding what the different failure mechanisms are, and how to gracefully fail if things go wrong. So if we take a step back and look at this migration as a whole, we could start to visualize some of the building blocks that would make up the workflow. We have our macro plan, which is what we wanted the general flow to look like, starting with a health check, interrogating the clusters for configuration info, a confirmation prompt, muting monitors, and finally migrating the nodes. Then we also have individual steps for migrating a single node, including another health check, updating replace address flags, alternating K8s resources, and monitoring for completion. Each of these bullets correspond to either a retriable activity or an entirely separate workflow. And as I said earlier, we valued reusable, adaptable components that could be linked together. Workflows are the building blocks of temporal, and by creating these sub-workflows, we were helping develop components that could be utilized in future workflows. The workflow on the right is something we actually still use today in our daily operations for cluster management. These steps are a real program, and a very complicated one at that. Building it required numerous designs, reviews, and many tests with a goal to constantly improve. Although our initial implementation automated a number of steps, there was still a process both for our team and the application team that occurred in tandem alongside the workflow. Our teams would sync to develop a migration plan, we'd bootstrap the new cluster, launch the workflow, confirm the plan, let it migrate some nodes, reconvene with the application team to update some config, launch the second half of the workflow, all while monitoring dashboards to ensure that there are no lapses in performance. The one thing to notice is that on our side, as the Cassandra team, we had a lot more steps here. But that's by design. We wanted migrations to be seamless, non-intrusive, and require minimal engineering hours from application teams to reduce the total burden of the migration and increase their team's confidence for future migrations. And that worked for a while, but we continued to iterate, and we had the incentive to do so, which was reducing our own burden for the migrations. We dogfooded our own tools, and we were constantly seeking to improve the pain points we were experiencing. In a later state shown here, the total amount of coordination and effort was greatly reduced and improved to the point where it was basically a single button press. We could reach out to the team and say, hey, just a heads up, we're going to move a bunch of your nodes in the background. Let us know if you see anything suspicious, but we don't need anything from you. And we could launch the workflow and let it migrate all the nodes behind the scenes. Improvements didn't just come from us. This was largely possible due to a service product from our traffic team that allowed nodes across different Kubernetes clusters to be discovered transparently. Improvements also came in the form of safety. We were launching a lot of migration workflows as well as workflows for daily operations, but we needed a way to stay out of each other's way. We're 6 teammates spread across 2 countries and multiple time zones and require plenty of coordination to avoid stepping on each other's toes. Enter distributed locks, a product created by a sister team which we were able to integrate into our workflows that ensured only a single workflow was operating on a Cassandra cluster at a given time. In conclusion, moving data is hard, but with tools like Temporal, it makes the job much more manageable. Doing this entire migration manually would have taken much more time and would have been much more susceptible to human error, although it was still not immune from the occasional fat finger. This quote really resonated with us when we were designing workflows. Creating workflows that were deterministic and creating idempotent activities reshaped the way we thought about our current runbooks and future ones as we wrote them specifically with automation in mind. What does our future look like? Migrations to more cloud-friendly infra, upgrades to new versions of Cassandra, or possibly even moves to alternative storage solutions. I can't say for sure what our future will look like, but I can say with some level of confidence that Temporal will help us automate our cluster-level operations. That doesn't mean that there won't be roadblocks along the way. As we develop these workflows for specific situations, they may eventually become unused and deprecated. We're proud to remove dead code and keep our repositories light, and it's okay to retire something, but there is a cost to clean up and untying dependencies. We can also envision a world where workflows get triggered automatically, maybe after a monitor fires. How can we be confident that the situation calls for that exact workflow and not something else? These are questions we have to ask ourselves. Temporal can solve a lot of problems, and it's greatly reduced our dedicated ops time. And it's natural to want to automate all the things, but it doesn't mean it can or should solve every problem. Thank you.
Any questions?
When you're looking at like the operator versus like enhancing the operator versus putting something into temporal, how do you make that decision?
That's a great question. I think one clear, like if it depends on something that is not in Kubernetes, like typically some monitor or some external resources, we are not going to use the operator. There's also something related to the release process. Releasing your workflow is rather easy. It's just about deploying a single worker. If you get it wrong, you can revert easily. If you enhance your operator, you're just like committing to something deeper. So that's how I would, determine whether I want one or the other. As of today, most workflows are for something rather out of the norm. That is, you do it regularly, but ideally you would never do it. Ideally, I would never replace a node. I mean, why would I do that? But I need to do it.
I don't know, pretty basic question, but what impact have your customers seen based on the implementation? Or have you actually seen anything really in terms of, customers able to access their data, see their dashboards? That's probably something you can't answer, but.
I think honestly, the impact has been mostly positive, or maybe nothing. I think like the real good thing has been on our side, on the ops side. Typically, like the migration example Steve mentioned, we used to do migrations before. Like I've had been doing some primitive Cassandra operations before, and it was painful. And also, you have this mental pressure of, I need to think tomorrow that I need to clean up this thing and not forget this step or that step. So I think that the progress was really for us as operators. And then, if we're not spending time on the users' things, that means that we're spending time on the right things that make the service better. I think for our customers, the change is really there. Like we're doing the right thing and we're doing useful things as opposed to wasting our time on useless tasks like repetitive tasks at which humans are not great. At least I am not great at doing this. Workflows are better than me.
So I wanted to ask, when you switched your workflow to being a simpler process for your team, it seemed like you'd skipped the step for informing the customer teams that you had a new host in, which made me wonder if you'd switched to a different form of discovery for your clusters.
Yeah, so that was due to a service product by our traffic team, which basically had a DNS address that could resolve to either of our clusters at a given time. So from their perspective, they were connecting to one address, but what was behind that address was completely transparent to them. So we could control what the infra was behind and move the entire cluster without their DNS address changing.
Oh, without their address, because I was going to ask, did you find switching to DNS cause you any loss in availability or resiliency?
No, we had very little, I'd say, like loss of availability during these migrations. I think occasionally, if we migrated nodes and like somebody forgot to update the DNS address in the original versions, those were times where we would see that. Or if there was one node left and then we brought that one down, they would immediately lose access to it. So it's like small configuration changes like that, which is why that service product ended up being a nice win for us, because we were able to not have to interact with the application team. and could reduce their time of saying, okay, let's make this change, let's roll this deployment out to all of our data centers and verify everything before we can finish the rest of the migration.
Great, thanks.
But just to add a little bit, something that was complicated is that due to the fact that Cassandra, exposes the topology to clients and to wherever you come from, it was complicated for us to just be 100% sure that they were using the right address and not a specific address, because the TCP traffic at some point is just like coming from anywhere. So we have ways to mitigate that, but that was a small issue, yes.
Any other questions?
So with that, thanks for your attention.
Yeah, thank you.
I'm just going to close this so that you don't judge all of my stuff. Yeah, well, I also have Premiere Pro. Oh, yeah, I should turn those off. You know what I'm going to totally turn off? That, thanks. Hang on. I can do it from my Apple Watch because I use all Apple products because they're awesome. I'm going to turn this into a do not disturb moment. I will not be disturbed. So Josh isn't going to send me random Slack messages. No, I shouldn't have said that. You know, you should. And then all kinds of bad things happen, like, dude, your flow's down. Oh, yeah, we all love each other here in the Cassandra community. Yeah, so I'm just going to start this thing off. Accord is the next great Bitcoin transaction protocol. That's right. This is your crypto bro path to happiness. And I'm going to talk about how you can make $1 million today with Accord. You didn't expect that, did you, Blake? Yeah, on the money, yeah. How's everyone's summit going? Is this good? We're almost through, right? Yeah, like, Day 2 is hard, huh? Because you burn hard the first day and you're like, I could do this 2 days. Then you wake up and you're like, no, I can't. Yeah, that's what I always feel like we should have like a day and a half conferences, like a 2-day late conference. And like reInvent is literally a week now. It's Sunday to Saturday now. What's that? A long morning? Like, yeah, we could do that too. Yeah. We start at 3 a.m. and end at noon. We'll start at midnight. I know some of you are probably like, that's the middle of the day for me. All right. 4:10. I think this is when I'm supposed to start. I don't know. I'm kind of losing track of time. So I'm supposed to be entertaining. Oh, man. Josh. Let's do this. All right. Everybody loves acid. Yes, it is. Funny, I just read an article about how Silicon Valley is the acid capital of the world. And I'm like, yeah, that's my talk tomorrow. Not that. All right. Yeah, I mean, come on. The jokes are easy, right? Let's just go. OK, so here's everybody. So when I've talked to any user about Cassandra since no, it was probably around 2011, 2012. This is the thing I keep hearing. Like, oh yeah, Cassandra's awesome, man. Uptime is awesome, scale is awesome, but I need transactions. And I get it. I mean, we all have lived, you know, we're like Barbies living in a Barbie world, right? We're living in like relational database world. I've been using relational databases since a long time ago. And that's what we all expect. They were built around ACID transactions, right? Oracle started this whole thing in the 80s, and it's just gone crazy since. So it's not weird. So we're just going to have to deal with this. So there are 3 use cases. I'm going to talk about 3 use cases, macro use cases, that Cassandra can't do yet. And this is what I've always had to talk around. Now, it's either you don't do it, or you make up something super crazy. Hey guys, how you doing? We've done that. You're like, oh, it doesn't have transactions? Let's use magic and code to make it work, right? And you can fake it, but you're putting a lot of work on yourself and not on the database. So number 1, bank transactions, the classic, right? Even though banks would actually work like this. You know, it's this thing of like exclusively moving from one table to another. That's the big deal, right? There's this order, like this thing happened before that. The exclusivity, you know, that it's only one person or one process making a change. Many of you know, because you were at dinner with me last night, this is a Midjourney image. I asked it to give me an Alice to Bob, and there's Alice giving Bob a big fat stack of Benjamins, but that's a transaction. This is a hard one, right? This is probably the number 1 thing that people talk about when they talk about transactions is like, oh, I want to be able to do a bank transaction. Because people love money, right? And money, if money gets lost, that's a data loss that hurts, right? Because if your bank loses your money, you're probably not going to work with that bank anymore. inventory management. And this is one that I think once you understand the problem, this is probably more of an issue with like inventory is being finite. So it's not that you have inventory, it's that eventually you're gonna go to zero. Good example is if I wanna buy a PlayStation 5 and there's only 5 left, you know, you all had this problem, right? Am I the only one? Right? The PlayStation 5, and there's 5 left and everybody clicked, who wins? Well, what you don't want is you find out that you now have negative 300 PS5s in inventory. That's just not that's not a normal number. It's not okay. So you need to be able to be precise and first come, first serve, and it's a high concurrency problem too. Like if you have one record in your database that says PlayStation 5 and here's your inventory count, that's a problem. So this is another issue that definitely stay away from. And then finally, the distributed ledger. I told you there's going to be Bitcoin in here. But actually, this is much more than just Bitcoin. It's a more generalized problem. It's like, and this is one that's really tough. It's like the changes have to be in order, but also it has to adhere to some sort of timing as well. This happened before that. And this is wall clock. If you talk about consensus protocols, there's the real time. Like if I'm sitting there looking at the clock and the second hand ticking, I want to know that the order is I clicked here, and then that person clicked here, I win, right? There's no funny math when it comes to time. Time is supposedly an arrow. So that's a really hard problem, is sticking to that. So what needs to change in Cassandra? Or I should say, what has changed in Cassandra? Because this has been, spoiler alert, this has been working, this has been happening for a while. So what needs to change? Well, this is a great, if you want to know more about consistency levels, I've been going back to this Jepson website for a long time, just because this is a really good explanation of consistency levels as you can find, because they're gathered in one place. And I love this chart. I've been using it for a while, and it just shows you the hierarchy. You know, the higher you go, the stronger the consistency. The lower you go down, YOLO. And you know, Cassandra has fit in various places in that, but really serializable. See, if you notice there's a fork in the road here, over here is linearizable, God, these words. And then serializable, I don't even think those are real words, but we made it a word. They fork off, they're two different things, right? Well, serializable is the one that is really the current limit of distributed databases where people are at. It's like, and these are like, the Spanners, Auroras, Cockroach, Yoga Byte. And the reason is because, and they're very clear, like you go to the Cockroach website, they'd say, hey, we are serializable, and this is why. Because to make it linear, it is super hard. And it's not that it's impossible, the costs are too high. Like to do it, it just takes too much time and resources. And users would have a terrible experience. So it's just a trade-off. It's not a terrible trade-off, but it is a trade-off. It's maintaining that strict sequence. So you don't have this race condition where one process overwrites another. And that current limited distributed databases is good enough for a lot of things, but not the best. And what we want to say, oh, that's the current limit. I'm sorry, my slide is messed up. It should say Cassandra, and what we're trying to accomplish with Cassandra with Accord is taking it all the way to the top, to strict serializable. So you get the strict sequence and the real-time ordering. And that's a pretty squishy word, strict serializable. There's a lot of definitions out there, but really the thing you need to understand is that it's not just the order of like when you did it, but it's also the wall clock time and maintaining that time order, which is a great way to not lose data in the long run. Because all of these, the only reason we care about consistency in a database is because we have situations that could lose data or have overwrite. And so the lower you go down, the more of those cases can happen. The higher you go up, and this is the best thing, is you can be super lazy. So the developer experience, as I said, is around this whole business of, you know, we in the Cassandra community have decided to put features lighter in the database at first. You know, it's very much, you know, put and get, but we put a lot of complexity on the developer. That has been evolving and changing for a while. And that's good, because what we're doing is we're making, because developers are like, yeah, no. Remember Thrift? It was awesome. But you had to really understand how to write good code to not destroy your data. So as we make more features available for the database, we make it easier for developers to write code against it. And it really just transfers all that complexity over to the database where it belongs. And it really is where databases have been for a while, right? I mean, I was an Oracle DBA, don't judge, but yeah, there was a lot of complexity put into that. And so whenever I wrote a very simple SQL command, I knew lots of stuff happened, but I also trusted it, right? Well, after like 9. 8 was, but after 9, it was totally solid. But you just trust what that does. But I didn't have to write a lot of complex code. I just threw it all in the databases and figured it out, right? And because I'm a lazy developer, right? As we all should be. We should all be lazy developers. And the difference, too, is this observer reference frame. And this is not a physics thing. This is about, like, as you're doing something with your application, you want to feel like, you're the only one there. This is what you want to feel like. And this is you. I'm the only one using the database, right? Even though there could be thousands and thousands of processes using the database. You don't want to have to think. I mean, if anyone's had to think through a race condition, yeah, I see the faces. Thinking through race conditions are hard because they're kind of amorphous and weird, and they usually aren't firmed up. Like, there's no deterministic way to say this is a race condition because they just occur, and that's why they suck. So let's just avoid that completely. You just want to look like you're the only person working on a database. All right, liven up, everyone. We're almost done. All right, so I talk about this a lot with this, but it is a thing. Pat Helland, I love this article. Like, this uncoordinated business is like, the more we have to think about coordination, the worse off we are, because it is a hard problem. It requires a lot of thinking. So just start working on uncoordinated as possible, because coordination is expensive. It is the most expensive operation you do on a database. That's why whenever we write data into Cassandra at a consistency level of 1, it's super cheap, right? What's the fastest way? Well, any. Don't use any. But 1 is fast, right? And why? Because it just YOLOs the data right into the database and just drops it in and doesn't do anything to check it. It really comes right back. Great. And that's a very cheap operation because it's a single node operation mostly. And when you start thinking about all the coordination that needs to happen, it gets really expensive. So we don't want that. So that we need to have a single system experience with a distributed system. And I'm not saying it's the holy grail, but I'm saying it's pretty tough. So back in the day, 1989 to be exact. Yeah, that's right. Top movie in 1989 was Lethal Weapon 2, and behold, Paxos. I saw Lethal Weapon. I didn't know about Paxos in '89. So, okay. But Paxos is actually, if I look at it now, after years of looking at it, it's actually not too hard. It's easy to reason through. It's impossible to implement. I think we just nailed it in the Cassandra project this week, last week. It's been a process, right? But it's kind of the headwaters of all consensus protocols. Paxos, right, back in the day. And it's this thing like, if one system in the distributed system says, hey, I want to make a change, it proposes that to everyone else. All the other nodes are like, cool. And then if it gets a cool back from everybody, it does it. And if one says no, then it starts again. So, but it's a consensus protocol, meaning it has to get consensus. You can't have naysayers, right? And Blake, remember that time we argued about ePaxos? Oh yeah, that's where I got my Paxos knowledge back in the day. We had a great time arguing about it. You won, by the way. But Paxos it's not an overly complicated thing, but when you look at it, you're like, oh, there could be a lot going on there. Yes, that's actually true. It can go back and forth. You can have, like, under high contention, like there's one thing that everybody's trying to change, all the processes are trying to change, it can get really noisy, right? Because everyone's like, I want to change it, I want to change it, I want to change it. And they overlap, and they're like, no, yes, no. It's like Congress. Anyway, Spanner saved us all. Just kidding. Spanner was a good idea. 2012, when that came out, a little later than Paxos. But Spanner is really just multi-Paxos. And the Paxos still applies, but it uses some method to make sure that from one Paxos domain to another, it maintains that sequencing, that serialization. The spanner, like the Google spanner, they have their own, true time, some atomic clock sitting in like a dark room somewhere. But there are other databases that use the spanner protocol or spanner paper. They're derivative, like Cockroach is a good example, where they said, hey, we don't have atomic clocks, right? So they implemented their own way to keep things synchronized. I believe they use vector clocks. And then Yogabyte is also a spanner, but they used another thing as well. So it's all kind of based on the same things. You have these multi-Paxos, and then you have this coordination layer. What that means is inserts can be really expensive. And I think that is the downside of spanner. Reads are not that hard because you turn into read replicas. But that's really bad for Cassandra because, and this is why I'm going to point that out, is because it creates this unnatural situation for Cassandra. Now we have to do all this massive coordination between data centers, which it's too much. We want to think about in terms of we want to scale the way we want to scale, add a node. We want to do 5 data centers, not just 2. And we don't want to have to change up your data modeling. You can't change that partition key because it's in a different data center. Those are weird things we'll start throwing at users. Remember, developer experience is a good thing. The easier it is to use, the less mistakes you'll make. So Accord, and I know there's probably something wrong on here yet, but keep it really high level. It really was designed for Cassandra, the way Cassandra works. And it's just leaderless, it scales like Cassandra, the failure modes match up. And that's one of the things with consensus protocols, which are really hard. What happens when you have a failure? A node goes offline. You don't want to have to stop everything, hold on, and re-elect the leader and come back online. That is not a Cassandra experience. We want it so that, and y'all love to talk about it, but it's a thing, and I'm going to bring it back with Accord. I'm going to start destroying Raspberry Pis with a hammer because that's the experience you want, right? You want to have lightning strike your data center and not have any downtime, right? That's the dream we should all have, and Cassandra can do that. But we shouldn't say, oh, but if you want ACID transactions, then all that's out the door. That's super lame. Let's not do that. So what about usage? Let's get into using it. Look at my clock. We're doing good. All right. How do we use, what is it about Accord and what we do with ACID transactions with Cassandra? There is some syntax. Stand by. And I think that this is still pretty firm. If not the case, I don't know, Blake, Ariel, somebody tell me I'm wrong. Caleb, I think you're in here too. But anyway, this is the current version. And what's new is adding this begin transaction, commit transaction. That's your block, right? That's your thing that says inside of here, ACID do occur. And inside of it, I'm going to break that down a bit too. First things first, there's a way that we can collect this current state of the data before we do a mutation. And that's this let command and you can put it into a tuple and basically do a pre-select of what am I going to change? And this comes in handy in a minute. You can also do a select that will show you the change after you run if this is successful. So this is like a before and after setup. This is where all the magic occurs. And it's really cool. We have this if statement that checks that tuple condition. So that's why we grabbed that tuple. So we can look at what was the state of that data and then make a decision. Now, I will walk you through some examples that will bring this home. But like I said, this is where the magic is, because when you have this conditional, and then inside of that, you can have updates, inserts, deletes. That conditional is where you make some really interesting decisions around things. This is going to come in super handy for a lot of things like inventory control. So I'm going to walk you through a couple use cases here. The bank transaction, right? Here we go. Alice is going to give Bob some money. So here's my setup. Here's my table. I have an account table, and just real simple. I have who has the money and how much money do they have, and I'm giving Alice and Bob $100, 100 decimals. You know, the real money that you can use. Probably Bitcoin at this point, right? Crypto. So if they both have 100, I'm going to walk through the transaction. So the first thing I'm going to do is I'm going to grab Alice's, because I'm moving money from Alice to Bob, I'm going to grab Alice's bank balance. Like how much does Alice have an account? I'm also going to emit how much, after it's done, how much Alice has after the transaction. Like I said, this is where the magic is. What I'm going to do is, because I'm going to move $20 from Alice to Bob, right? I want to make sure that Alice has that money in there. I do not want to overdraw. I know this is not a really good bank thing. Of course banks want to overdraw you because that's how they make money, right? But anyway, let's just imagine that we're a good bank. We don't want to have our people overdraw. So we don't want to overdraw the account. So what we do is we check to see if that account balance is greater than or equal to 20. If it is, Alice has enough money to give Bob, and it happens. So if you look over here, you see the update. There's two updates that happen. There's another syntax that I absolutely love. Now the update can do a plus equals, minus equals. Blake's smiling because he knows I love this so much. I wish we just had this in the regular syntax, by the way, and so does Aaron. But if we just do able to increment, we can increment this in place. So we'd say an update. So take $20 from Alice, give $20 to Bob. That all happens wrapped up in a transaction. I commit the transaction, we're done. Now, before you ask, no, there's no rollback. I know. You want to leave? All right, I'll keep going. Rollback's a different problem. Inventory management. This one is also super cool because this is one I've never been able to solve well with Cassandra. It just is a super hard problem. It's an intractable problem for many cases. So I have some products in a product table. I have my shopping cart. Probably all of you have created this at one point in your life. So I'm going to insert that PlayStation 5. I'm going to put 100 PlayStation 5s into the product because probably that's not even how many were there back in the day. It was weird. Like they would get like Best Buy would get 20, Walmart would get 20. Like what? Did they meet somewhere? But anyway, limited inventory. There's only 100. Now, what I'm going to do, same type of thing, setup. I'm going to look to see what the current inventory is. And this is all locked. When I start this transaction, this is all locked now. I'm going to look at the current inventory for PlayStation 5s. I'm going to emit the inventory after I'm done. But then, again, this is where I make sure that I don't go past 0. So if the inventory is greater than 0, then I'm going to update, I'm going to change the inventory, decrement it down 1. So there's one less PlayStation in the world. And then I'm going to insert it into my shopping cart. Yes, I got a PlayStation. But yeah, I know. Thanks, Max. But that's all happening in a transaction and locked under a highly concurrent workload. All those idiots clicking on the buy button, right? It's going to be OK. Relax, because the database has got you. And that's impossible to do without it being in the database. I'm just going to say that. It's impossible. It needs to be closer to the wire, where the data exists. And what this does, so in a highly contended load, if I had, here's where the order and the linearity comes in. If I have two people that click really close to each other, they're still milliseconds apart. So, because Max was really excited too, and he was just a millisecond late, I got the PlayStation. Sorry, Max. Sorry. Last one. But, you know, wah-wah. You don't want to send your customer an email saying, sorry, we totally blew past the inventory. Here's a coupon. Is that what you guys do at Walmart? Yeah, pretty much, yeah. But think about, like, this isn't just shopping cart or inventory. Think about other things where this applies. Again, these are general patterns, but a good example of how this works. I built this thing as funny as like, yeah, I want to make this to sell my book. But Yeah, I can't even give them away, so there's still 10 in inventory. So, but this is like the thing that I think about is like, oh, the Thundering Herd app. Like people are like, get it now, click. This used to be scary, now it's not. Now, I don't have a really good distributed ledger one. I actually was trying to come up with a really good one. Yes, that's an interesting problem. Yes, that's one we can't do with Cassandra, but I actually want to go after something that has been impossible to do well, that I think has more applicability for the Cassandra community, which is this real atomic batch. Now, when I say real, some of you may realize that there was a controversy or know about this controversy. There at one point, somewhere in the docs, the batch in Cassandra was called atomic. Yeah, you want to start a fight in the Cassandra mailing list, call it atomic batches. Oh, people start throwing out definitions. That's not atomic. And of course, they weren't really. It just got named that, and unfortunate naming. But I'm here to save the day. I'm going to be a peacemaker. You can actually do it now. So think of this, and this is a very common pattern in Cassandra where you have a base table like a user, but then you create lookup tables, user by email, user by location. Now, these are index tables. Now, if I was to change something in my user record, like their city or by their email address or something like that, I need to update the index tables as well. Now, you could do that with a batch, but the batch is non-deterministic, right? It will eventually happen. It's eventually consistent, but it isn't a ACID transaction. I'm not changing all my tables at the same time. And what this is the same thing. I'm going to check. I'm going to say, does this person even exist? So I'm going to make sure not do anything that doesn't exist. And this is that example of that, if the tuple is null, right? That is an interesting problem, right? So what I'm doing is I'm actually creating a situation where if this person exists, I'm not going to stomp on them. But if the account doesn't exist, then I'm going to create a brand new one. Now, I can also do updates, like if I wanted to change my account, that would be a different conditional. But in this case, what I'm doing is making sure that lightweight transactions, let me quickly stop here. Lightweight transactions do this for one partition. If you need to do more than one, wah wah. So this is how you do that multi-partition change. And it's just built into the database. So cool. Okay, doing great on time. So when can I get it? Ariel, thank you. CP15 Accord, it's a branch right now. You can go download it and build it yourself. If you need help with that, hit me up. I was going to build a Docker image, but I didn't get time because I was hanging out with you guys, but which was worth it. It's all good. But I think I'm going to still do that. Maybe this weekend if I have time. But no, I want to create a Docker image around this because it's not a part of any official release right now, so I have to do it as an individual, not as official project thing. But the target release is 5.1. As you heard me maybe say this in the keynote yesterday, it was originally slated for 5.0. After some discussion in the mailing list, some light banter back and forth, some easy discussion about like differences between one version or another, because we just love each other in the mailing list, and this is what we do. We decided that we're going to decouple the Accord and transactional cluster metadata, TCM, from 5.0 just to let 5.0 ship. It's got everything. So it's in beta right now. Go play with it. But 5.1 will have, there'll be a fast follow and we'll have the Accord in that. But I mean, it's just a matter of, I think the important thing is that we all realize that this is a major change to Cassandra. Was like 88,000 lines of code got touched, or does that seem like a number? Anybody want to say yes or no? No, that was just TCM. Just TCM was 18. So yeah, it's a big one. But when you touch that much code in any consensus protocol, we want to really make sure we test it a lot and make sure, because we as a project, and we hold dear quality, right? And that's important. And that's what we all agreed to in the mailing list. No, it's a matter of just making sure to give it enough room. And that, I think that's fine. But I do think it's important for everyone who's interested in using transactions with their next application to get out there and start getting used to the syntax, because it is different. You're going to have to learn about it. You're going to have to figure out how it fits in your application, and just, you know, it's just knowing how it works. Now, understanding that, you know, trusting it beyond the way, there's a lot of testing going on, that sort of thing, but just get the syntax right. I think that's what I want to recommend. This QR code goes directly to that branch if you want to go to there. And then finally, thank you very much. I think I nailed the timing. Max, questions?
I have 3 questions. I probably asked this most important one. So, transactions sounds good. Is there a chance we're going to see like transaction templates or the name like storage procedures in Cassandra in the upcoming years?
Transaction template. What I would really, really love to see is find its way into some frameworks. Like, you know, there's a lot of frameworks now. You know, Aaron's talked about Mongoose, for instance. Mongoose is a JavaScript framework for Cassandra. I just think that would be cool to see that just magically get awesomer. But under the covers, it's using transactions. So no particular templates in Cassandra, but I think I would like to see this go out into the ecosystem and just become more of that. Spring is another one. Spring Data has some hooks in it that I would love to now be able to use. That's a good example. Yeah. Second question?
Yeah, another question.
Let me have you just
Oh, yeah.
captured on the streets.
Yeah, thank you for the mic. Second question. I trust you created a lot of different ways to check the condition, but is there a chance that at some point of time we are going to be able to upload our jar to Cassandra and do very complicated checks for the condition before we enter the locked state?
A very complicated check. Like, what would be an example of a complicated check? Like a subselect, maybe? Or no, you already do a select off your data. So anything that's supported in a select statement is available. You can create a tuple with.
What if we have some, you know, complicated math around with math functions which are not supported?
Oh, yeah. I don't know if that's really, does anyone know? I mean, like if you wanted to do like a max or a min or something like that, is that what you're talking about? Like math functions?
Yeah, math functions, but maybe more complicated than just max and min. You know.
Or a count is another one that could be done. Like how many of these things? Yeah, I know. I got everyone laughing at me. Like, oh God, here it comes. See, you should never release code because now everyone wants more, right? There's no plans right now, but this is where I encourage you as a user of the system to join us in the Apache Software Foundation Slack. There is one called Cassandra Accord. Right now, it's just a bunch of people trying to figure out how to compile it and make it work, and there's a lot of stuff that's going in there about the details. But I would love to see that transition more to, hey, I'm using it, and here's my experience.
One thing I will say is historically when we have like user-defined functions or jars that ship out and execute arbitrarily in the node context, it's a massive surface area for security problems.
Yeah.
So it's historically been pretty challenging to thread that needle and provide support for that kind of thing.
Yeah.
Please file a Jira ticket sharing what you would like to do. This will help the community prioritize where we focus.
Yeah, Jiras are awesome because, and whenever you create a Jira, and I'll say this because the camera's on, when you create a Jira, you can say what subsystem it is, and you can say, yeah, this is for Accord. And yes, those are very valuable because first of all, it's official, it's in the system, and it can be followed up on, it can be routed, assigned, all these things. So Jira system is very good for, this is what we use in our Cassandra project. I think we're kind of out of, do you have one more question over here? Yeah. Tobias.
So I noticed all of your examples had a single let. Is
Yes.
it possible to have more than one let?
Yes, you can have more than one let.
Awesome. So is there, what's the limit?
You know, I don't think we have one.
Ah, nice.
Yeah, this is, well, welcome to the world of guardrails. We have not defined any for Accord yet. Yeah, guardrails is a 5 or a 4.0 concept, but yeah, I think that part of this is we're going to find guardrails. Right now, it's a little like go for it and let's see where it breaks. So Yeah, I expect we're going to find somebody. What do you mean I can't do 10,000 lets? Well, that's unusable. All right. Thank you very much. We'll be outside, but thank you.